Hello there and welcome to Physics with William, where curiosity gets cosy and science takes the scenic route to sleep. Tonight we are settling in with a question that sounds simple at first, then starts to behave in a very suspicious way the longer you look at it. What is an electron really made of? It is one of those questions that seems as though it ought to have a tidy answer waiting in a textbook somewhere, perhaps filed neatly between electricity and atoms. But once you start following it, the ground shifts a little. You begin with something familiar, something ordinary, maybe the glow of a bedside lamp, the warmth from a phone charger, the soft hum inside a wall outlet, and before long you are standing at the edge of one of the strangest ideas in modern physics, trying to decide whether the electron is a tiny object, a ripple, a point, a piece of something deeper, or perhaps a sign that our everyday idea of what things are made of was never quite right to begin with. Before we wander too far into that mystery, I would love to know where you're listening from tonight, or this morning, or perhaps in that slightly uncertain part of the day when you're not entirely sure whether it still counts as evening. And if you happen to know the time where you are, that makes the question even nicer somehow. A conversation about electrons has a charming way of taking place across cities, countries, and time zones, with each of us sitting among objects built from the same tiny ingredients, all asking what one of those ingredients actually is. It is a pleasant thought. Different rooms, different lamps, different mugs of tea, different levels of drowsiness, and yet the same electrons moving through all of it, keeping the world quietly stitched together. If you find this soothing, or interesting, or simply a decent excuse to let your brain settle into something gentle for a while, do consider liking the video and subscribing to the channel. It helps this little corner of calm science reach more people who might enjoy ending their day with a strange question rather than another email, and as always, I will do my best not to make this so fascinating that it keeps you wide awake. Though in fairness, if you do end up lying there later, staring at the ceiling and wondering whether an electron is a thing or a behaviour, you would not be the first, and you will be in very respectable company. Now then, let us begin in a place that feels solid, the sort of solid place your mind naturally trusts. Imagine the room you're in, the walls, the chair, the blanket, the floor, the phone or computer screen, perhaps a glass of water on the table nearby. It all seems made of matter in the most straightforward sense of the word. Stuff, things, objects with surfaces and weight and shape. You can tap the table, you can hold the mug, you can set the book down and pick it up again. The world presents itself as dependable and physical, which is very considerate of it. But physics, as it often does, takes that comfortable first impression and starts asking impolite questions. What is the table made of? Wood, perhaps. Fair enough. What is the wood made of? Molecules. And those molecules are made of atoms. That already feels a little more scientific and a little less like ordinary conversation, but still manageable. Atoms, after all, have become familiar enough in modern life that we say the word without much alarm. Yet once you arrive at the atom, the comfort starts to slip. Because the atom is not the end of the story. It is not a smallest brick in the wall of reality. It has its own interior life. There is a central nucleus made of protons and neutrons, and around it are electrons, which are somehow part of the atom and somehow not sitting inside the nucleus and somehow responsible for nearly all chemistry and electricity and bonding and much of the visible behaviour of matter, which is already a lot to ask of something so small. And the more you think about the electron, the stranger it becomes. It carries electric charge. It has mass, though not very much. It helps atoms form molecules, helps metals conduct electricity, helps magnets behave like magnets, helps screens glow and circuits function, and lightning flash across the sky. Without electrons, your body would not hold together the way it does, your nerves would not send signals the way they do, and your household appliances would become decorative in a very unhelpful way. This tiny entity is everywhere. It is involved in the ordinary business of the universe at every scale we care about. And yet when we ask what it is made of, physics becomes unexpectedly cautious. That caution is worth noticing, because science is often quite happy to answer direct questions. What is water made of? Hydrogen and oxygen. What is a proton made of? Smaller particles called quarks bound together in a particularly energetic arrangement. What is a chair made of? Materials, molecules, atoms, and enough regret from whoever had to assemble it. But what is an electron made of? There, the easy layering seems to stop. The familiar habit of opening one box and finding smaller boxes inside does not continue in the same tidy way, at least not according to our best present understanding. This is partly why electrons are so compelling, not because they are rare or dramatic, but because they are ordinary and mysterious at the same time. They are not exotic creatures hiding at the edge of the universe. They are here. They are in the air around you, in the wiring in the walls, in the chemistry of your cells, in the atoms of your skin, in the screen bringing you this video. If physics still has unanswered questions about the electron, then those questions are not about some distant curiosity. They are about the texture of reality close to home, and it is very tempting, very human, to assume that if something exists, it must be made of smaller parts. We do this almost automatically. A cake is made of ingredients. A house is made of bricks and timber and wires. A sentence is made of words. A watch is made of gears, or in the modern world, disappointingly fewer gears than one might hope. So the mind develops a habit. When faced with an object, ask what it is built from, then ask what those parts are built from, then keep going until you reach a final answer. It feels sensible. It feels methodical. It feels like the universe ought to reward that approach eventually. For a long time, that strategy worked rather well. Matter that looked continuous turned out to be made of atoms. Atoms that seemed fundamental turned out to contain nuclei and electrons. Protons and neutrons, once treated as basic, turned out to contain quarks. So it is not foolish at all to look at the electron and ask whether it too has an inner structure. Maybe there are smaller pieces inside it. Maybe there is some hidden machinery. Maybe the electron is not fundamental at all, merely another stop on the way down. The curious part is that every time physicists have looked for that internal structure, the electron has behaved, as far as we can tell, like a point-like particle, not point-like in the everyday sense, as though it were just very tiny, like a grain of dust only much smaller. Point-like in the much more unsettling sense that no size has been measured for it, no smaller components have been seen, no internal arrangement has revealed itself. It does not present an obvious surface or a little set of moving parts. It acts like something with no detectable width, in the way we usually imagine objects having width, which is the sort of statement that tends to make the brain stop, clear its throat, and ask whether perhaps we should all go back to discussing chairs. But the electron does not let us off that easily, because even calling it a particle comes with complications. In some experiments, it behaves in the way particles ought to behave, showing up in distinct interactions, arriving in countable bits, leaving tracks, transferring energy in tidy packets. In other situations, it behaves more like a wave spreading out, interfering with itself, refusing to behave like a tiny billiard ball with a fixed path. So even before we ask what it is made of, we discover that our everyday categories are already under strain. The electron is not simply a little bead of matter circling a nucleus like a planet around a star. That picture is historically useful, but physically misleading. Electrons belong to the quantum world, where nature seems to have little interest in preserving the common sense of large, sleepy mammals. Now that does not mean electrons are unreal or imaginary, or that physics has no idea what it is talking about. Quite the opposite. The electron is one of the most precisely tested ingredients in all of science. Its properties have been measured with extraordinary accuracy. Predictions involving electrons match experiments to a degree that would make most other fields of study sit down quietly and reconsider their standards. So this is not a case of scientific confusion in the sense of having no framework at all. It is a more interesting sort of confusion. We can predict what the electron does with tremendous precision, yet the deeper question of what it is, in the old intuitive sense of what it is made of, may be the wrong kind of question, or at least a question that needs rewriting. That rewriting is one of the recurring lessons of physics. Nature does not always answer the question we first ask. Sometimes it answers a better one after showing us why the first one was too tied to everyday habits. Ask what light is, and eventually you get an answer that does not fit neatly into the box-marked wave or the box-marked particle. Ask where time comes from, and physics becomes philosophical in a hurry. Ask what an electron is made of, and you may be forced to consider whether the very idea of being made of something is a concept that stops working at a certain depth. Still, let us not rush into the deep end too quickly. There is value in lingering for a moment with the feeling of the question itself. Suppose you hold a coin in your hand. It feels solid, complete, and ordinary. But that coin is made of atoms. The atoms contain electrons. Those electrons are helping determine the way the metal holds together, the way it reflects light, the way it feels cool at first touch and warmer a few moments later. They are essential to the character of the object, yet the electron itself does not seem to be a tiny coin inside the coin. It has no little shell, no visible seams, no obvious internal architecture. It is as if matter, once reduced far enough, stops resembling matter in the familiar sense and becomes something more abstract, more behaviour-based, more woven into the rules of the universe than assembled from miniature chunks. There is also something mildly amusing about the electron being both indispensable and elusive. It is a bit like having a co-worker who runs the entire office, understands every system, fixes every problem, never explains where they learned any of it, and vanishes the moment someone asks for documentation. The electron does not hide because it is rare. It hides because it is too fundamental to expose itself in the way we expect composite things to do. If it truly has no smaller pieces, then there is no inner machinery to uncover. There is only the electron being exactly what it is, full stop. However unsatisfying that may feel to a species that likes diagrams with labelled components. And perhaps that is why this topic has such staying power. It places us right at the border between description and understanding. We can describe the electron very well. We know how it behaves in fields, in atoms, in circuits, in collisions. We know its charge and mass. We know it belongs to a family of particles called leptons. We know it participates in some interactions and not others. We know it can be created and annihilated in certain processes. We know a great deal. Yet somewhere inside, all that knowledge remains a quiet discomfort. Yes, but what is it really? Not just what does it do, not just how do the equations treat it. What is the electron in the furniture of reality? That phrase, what is it really, is where much of the trouble begins because it sounds plain and honest while smuggling in an enormous amount of expectation. It assumes there must be a deeper, everyday style answer waiting underneath the scientific one. A hidden picture simple enough to hold in the mind like a tiny mechanism. But physics has spent the last century gently but firmly explaining that the universe is under no obligation to provide pictures that fit nicely into everyday intuition. It will provide reliable patterns, tested theories, astonishing regularities, and occasional existential discomfort. Beyond that, we negotiate. So tonight, as we ease into this question, it helps to hold two ideas together at once. The first is that the electron is real, measurable, and central to the structure of matter. The second is that its reality may not look like a little object built from smaller little objects. Those two facts can sit side by side even if the mind keeps trying to separate them. And once you accept that, even provisionally, a more interesting path opens up. Instead of insisting that the electron must be made of parts, we can ask how scientists came to discover it, why they first believed atoms were indivisible, what experiments forced matter to give up one of its secrets, and how the electron gradually transformed from a strange clue in electrical experiments into one of the basic entities of modern physics. Because there was a time when nobody knew electrons existed at all, Electricity was known as a phenomenon long before its underlying carriers were understood. Static shocks, lightning, glowing tubes, sparks from rubbed amber, all of these belonged to the story before the electron had a name or a place in theory. People could observe effects without knowing the microscopic actors involved. And that is often how science begins. First the behaviour, then the guess, then the argument, then the measurement, and only later the unsettling realisation that the answer is stranger than the question that started it. In that earlier world, matter still looked more solidly made than it does now. Atoms were often imagined as final units, the end of division, tiny indivisible building blocks. The word itself had carried that suggestion for ages, and in a way one can sympathise with the confidence. If you keep cutting matter down in imagination, eventually you reach something you think must be the smallest piece. It seems practical. It seems neat. It seems like the kind of idea the universe might permit out of courtesy. But nature is not especially tidy in that sense. Just when scientists started feeling comfortable with the atom as a final answer, experiments involving electricity and cathode rays began to suggest that the atom had internal components after all. And that was the beginning of a very important discomfort. Because once a supposedly indivisible thing turns out to contain parts, a door opens that is hard to shut. You begin to suspect that every ending may only be a pause. Every smallest thing may just be the smallest thing so far. Every neat answer may be a temporary arrangement awaiting a brighter lamp and a more precise instrument. The electron entered physics through that door, not as a polished philosophical idea, but as evidence that the atom was not the final layer people had hoped it might be. That is where the story becomes especially human and especially worth telling slowly. There were glass tubes, mysterious glows, arguments over what exactly was moving through them, and a gradual shift from vague electrical effects to the realization that something universal was being uncovered, something present in matter itself, something smaller than the atom. And once that something was identified, the old picture of matter could never quite be put back together in the same comfortable way again. So as we continue, keep the main question nearby, but do not expect it to answer itself all at once. What is an electron really made of is not the sort of thing physics resolves in a single neat sentence before bed. It is the kind of question that asks first for patience, then for history, then for a willingness to let ordinary intuition loosen its grip a little. And the first step is not to jump straight to modern theories of quantum fields and fundamental particles, tempting though that is. The first step is to return to the moment when matter first began to reveal that it had a hidden interior, and when scientists, peering into curious electrical phenomena, started to realize they had found something astonishingly small, astonishingly common, and much stranger than a tiny speck ought to be. What makes the electron such a good place to linger is that it is not hiding in some remote corner of physics, tucked away inside a machine the size of a city, or buried under a mountain where only a handful of people in special helmets ever get to meet it. It is involved in almost everything around you right now. The screen in front of you depends on electrons. The light in the room depends on electrons. The chemistry in your body depends on electrons. The air, the table, the walls, the fibres in your clothes, the metals in your charger, the salt in your blood, the signals moving through your nervous system, all of it is tied in one way or another to the behaviour of electrons. So when we ask what an electron really is, we're not stepping away from ordinary life into some separate scientific universe. We are looking more closely at the ordinary life we already have, and finding that it is assembled from something much stranger than it first appears. That is one of the nice little tricks of physics. It starts by sounding as though it is going to tell you about objects too small to matter, and then very calmly explains that those objects are the reason anything matters in the first place. The word tiny makes it sound optional, almost decorative, like a small button on a jacket or a raisin in a cake that nobody asked for. But the electron is not tiny in the sense of being insignificant. It is tiny in the sense that you cannot pick one up, point to it directly with your eyes, or tuck one safely into a pocket for later. Its importance is not reduced by its size. In fact, much of the character of the visible world comes from the fact that electrons behave exactly the way they do. Take something simple, like a wooden table. You can knock on it and hear the sound. You can rest your hand on it and feel that it is firm. You can put a cup on it and trust, with reasonable confidence, that the cup will not fall through and ruin the evening. This all feels very direct. The table is solid because it is there. End of story. But the deeper account is much less straightforward and much more interesting. The atoms in the table contain electrons, and the way those electrons are arranged around the nuclei of those atoms determines how the atoms bind together into molecules, and how those molecules build larger structures. Even the feeling of solidity, that sense of your hand meeting resistance when it touches the table, is not some simple meeting of hard little pebbles. It comes from electromagnetic interactions, from the behaviour of electrons and the rules that govern how they can and cannot occupy the same states. In a very real sense, when you touch the table, you are not making contact in the old intuitive picture of objects pressing directly together like billiard balls. You're encountering a complicated electron-based refusal. The universe is saying, in a very polite but firm way, no, those arrangements do not overlap like that. Which means the everyday experience of solid matter is already a clue. The world feels sturdy not because matter is made of miniature solid chunks, stacked tightly like bricks in a neat warehouse, but because electrons create patterns of structure, bonding, and resistance. The things we call physical are physical, partly because electrons make them behave that way. That alone makes the electron worth our attention. It is not just one ingredient among many. It is one of the main reasons the material world has texture, strength, colour, and chemistry. Colour is another lovely example. If you look around the room, you see different surfaces reflecting different kinds of light. The blanket may be dark, the wall may be pale, a book cover may be blue or green or some shade. The paint company insists on calling morning fog, which sounds more like a light inconvenience than a colour. Those visible differences are deeply tied to electrons. Light interacts with the electrons in atoms and molecules. The allowed ways electrons can absorb or release energy help determine which wavelengths of light are taken in and which are reflected back toward your eyes. So when you notice the colour of a curtain or a mug or a leaf outside the window, you're seeing electron behaviour expressed on a human scale. The electron is not just hidden inside matter, it is quietly helping matter announce itself. Then there is chemistry, and here the electron becomes even harder to avoid. Chemistry is often introduced as the study of substances and reactions, which is true enough, but under the surface it is very largely a study of how electrons are arranged, shared, exchanged, or redistributed. Why does oxygen react so readily with some things? Why does sodium behave so differently from neon? Why do carbon atoms form such a vast range of molecules that life can be built from them? Again and again the answer comes back to electrons, especially the electrons on the outer parts of atoms, the ones most involved in bonding. These outer electrons help decide whether atoms attract one another, ignore one another, cling tightly, or swap partners in a way that makes an entire chemistry lesson feel faintly social. And because chemistry underlies biology, the electron ends up being involved in the business of life as well. The molecules in your cells are held together by chemical bonds. The proteins in your body fold into shapes because of interactions that depend on electrons. Your muscles contract through processes driven by chemical gradients and charged particles. Your neurons fire because electrical signals move across membranes in carefully regulated ways. Breathing, eating, thinking, remembering, all of it depends on structures and reactions in which electrons play a central role. The human body can sound very grand when described in everyday terms. A thinking being, a conscious creature, a self-aware arrangement of matter wondering about the foundations of reality while adjusting a pillow. But at the working level, electrons are busy in nearly every corner of the story. The same goes for modern technology, which has found more ways than seems fair to recruit the electron into service. In metal wires, some electrons can move relatively freely, which is why metals conduct electricity so well. The electric current powering a lamp or a laptop depends on electron motion. In electronic components, the control of electron flow allows us to build circuits, processors, memory devices, sensors, and communication systems. Your phone is not full of miniature little people doing calculations at impossible speed, tempting as that explanation may sometimes be. It relies on carefully engineered materials that guide electrons in precise ways. The digital world, for all its glowing sleekness, is still built on the patient management of tiny charged entities behaving according to quantum rules. Even magnetism, that slightly magical force that lets one object tug on another without any visible rope between them, is tied to electrons. Their charge matters, of course, but so does another property they possess, one we will come to later in more detail. What matters here is that much of the magnetic behaviour of materials comes from how electrons are arranged and how their intrinsic properties line up. So the next time a magnet clings to a refrigerator door with a sort of cheerful confidence, it is worth remembering that the effect belongs to the same deep family of electron behaviour that also helps atoms hold together and helps electricity move through wires. The electron does not merely participate in one small corner of physics, it turns up in matter, light, chemistry, electronics, and magnetism, as though determined to make itself indispensable. There is something else that makes the electron especially interesting. Unlike a chair, a cloud, or a cat, an electron is not different from one place to another in the way large objects are. Electrons are identical. The electron in a copper wire and the electron in an atom of oxygen are not cousins with slightly different personalities. They are the same kind of thing in the strongest possible sense. One electron is like another electron. This sounds modest at first, but it has huge consequences. It means nature has a kind of deep consistency built into it. The same electron behaviour can show up anywhere in the universe. The electrons in a distant galaxy follow the same basic rules as the electrons in the atoms of your hand. Reality is not improvising a new version each time. It is using the same ingredient again and again with enormous reliability. That reliability is part of what allows physics to be physics at all. If electrons behaved one way on Tuesdays and another way near a fruit bowl, the scientific method would become very tired very quickly. But they do not. They are stable in their identity, stable in their charge, stable in the role they play in ordinary matter. This gives the universe a kind of repeatability. The fact that hydrogen here behaves like hydrogen elsewhere is one reason stars can shine, according to rules we can study. The fact that electrons are universal is one reason the same kinds of atoms can form throughout the cosmos. So when we say the electron is hiding inside nearly everything, that almost undersells it. It is not just widely present, it is one of the common threads stitching the visible universe together, and yet it remains difficult to picture properly. That is perhaps because our instincts were trained on large things. We know what it means for a cup to be made of ceramic, or for a loaf of bread to be made of flour and water and perhaps too much optimism. We know what it means for a machine to be made of parts, but the electron resists being imagined in those familiar terms. It is not a little hard marble orbiting inside atoms in a tiny solar system. That image had historical value because it helped early learners grasp the idea that atoms have structure, but it quickly breaks down. Real electrons are not miniature planets with neat tracks. In atoms, they occupy quantum states. They are described by patterns that give probabilities for where they may be found. Their behaviour is governed by rules that do not resemble the behaviour of pebbles or grains of sand. So although the electron is everywhere, the mind does not get the luxury of treating it as a familiar everywhere. It is more like an everywhere that behaves with impeccable strangeness. That strangeness shows up even in the fact that atoms are mostly empty space in the old geometric sense. The nucleus is tiny compared with the whole atom. Electrons are not packed in like stuffing in a cushion, and yet matter does not feel empty. A steel beam does not feel like a ghost. A stone does not feel like a rumour. The reason is that the structure and behaviour of electrons make matter act solid and substantial, even when the old image of densely packed little balls would be misleading, which means the electron is central not only to what matter is made of, but to why matter feels the way it does to creatures our size. It is also worth noticing that the electron lives a double life in our thinking. On one hand, it is an object of careful physics, measured in laboratories and described with extraordinary precision. On the other hand, it is part of the scenery of everyday existence, whether we think about it or not. Most of us do not wake up and say, "Good morning to the charged leptons that are helping hold my breakfast together." We simply get on with the toast. Yet the toast, the toaster, the heating elements, the smell, the browning chemistry, the electrical current in the wall, all of it involves electrons. They are among the least celebrated workers in nature. There should perhaps be a holiday, though they would probably ignore it and continue being fundamental. Then again, one of the reasons we overlook electrons is that they do not appear alone in daily life. We meet them through their effects. We meet them through matter, through electricity, through chemical change, through light and magnetism. In that sense, the electron is almost too successful at blending into the world. It hides by being everywhere at once. If something rare shows up, people point and gather around. If something is present in nearly every ordinary object and process, it begins to disappear into normality. We stop seeing it as discovery and start seeing it as background. That is why questions like this are so useful. They take what has become ordinary and restore its mystery. Consider again the simplest household scene. A lamp glows. Why? Because electrical energy is being transferred through a system in which electron behaviour matters. A metal spoon feels cool. Why? Because heat moves through matter in ways tied to the structure and motion of particles, including electrons. A leaf looks green. Why? Because molecules in the leaf interact with light in a way determined by electrons. Sugar dissolves in tea, iron rusts, batteries discharge, bread browns. A static shock jumps when you touch a doorknob after walking across a carpet. All of these are familiar little events. None of them announces itself with orchestral music as a profound clue about reality. And yet each one is part of the electron story. There is a special pleasure in realizing that what seems ordinary is often only ordinary because it happens constantly. If lightning were as common as rain, we would complain about it ruining the washing and move on. The electron has become normal to us not because it is simple, but because it is deeply woven into the normal. It is part of why the normal exists. Once you see that, the question changes shape a little. Asking what an electron is made of no longer sounds like a narrow technical problem. It sounds like a question about how the visible world acquires its behaviour from ingredients that are not visible in the same way. This also helps explain why physics cares so much about whether the electron is fundamental. If it truly has no smaller pieces, then one of the universe's most important ingredients is not built from deeper material, in the way a molecule is built from atoms, or a proton is built from quarks. That would mean the chain of what things are made of does not continue in the same style forever. At some point, at least according to present evidence, the descent reaches entities that do not look assembled. They simply are, not because physicists gave up looking, but because experiments so far have not revealed substructure. The electron in this picture is one of the basic entries in nature inventory. Of course, human curiosity does not retire gracefully at that point. It leans forward and asks whether that can really be the end of it. Surely something this important must be made of something. Surely there must be another layer. Perhaps. Physics is careful here. It does not say the electron cannot possibly have deeper structure. Science is not in the business of issuing eternal proclamations from a marble balcony. It says that according to everything we have observed with our best current theories and experiments, the electron behaves as a fundamental particle. No internal pieces have been seen. No size has been measured. No smaller machinery has announced itself. The safest answer is not that mystery is gone. but that mystery has become more disciplined, and in a way that makes the electron even more impressive. It is not only widespread, it is so far irreducible. The same entity that helps your phone charge, your heart beat, and metals conduct may also be one of the true basic ingredients of reality. That is a remarkable promotion for something most of us only meet by name in school, and then spend years associating mainly with diagrams and mild anxiety. Still, it was not always obvious that matter contained anything like the electron at all. For most of human history, nobody walked around saying that the world was full of tiny negatively charged entities, helping determine chemistry and electricity. People could observe electrical effects without knowing what lay behind them. They could see amber attract bits of straw after rubbing. They could watch lightning split the sky. They could notice shocks, sparks, glows, and magnetic oddities. But the hidden agents inside matter remained hidden. The electron was doing its work long before it had an audience. That is where the story begins to shift from everyday presence to discovery. Once you appreciate that electrons are bound up with nearly everything you can touch, see, switch on, breathe in, or build, the obvious next question becomes how anyone first managed to notice them at all. After all, they are not sitting around with labels attached. Nobody opens a drawer and finds a neat row of electrons arranged by size and temperament. Scientists had to infer their existence from effects, from experiments, from strange behavior in electrical apparatus that slowly revealed matter had more going on inside it than anyone had suspected. And that moment, when the old picture of the atom began to crack and something small appeared through, is where the quiet ubiquity of the electron finally became impossible to ignore. There was a long stretch of human thought in which matter seemed to offer a fairly satisfying answer to the question of what things are made of. Not a perfect answer, of course, because human beings have never been able to leave a good mystery alone for very long, but a satisfying one by the standards of its time. If you kept breaking a thing down in your imagination, from a rock to grains, from grains to smaller pieces, from those pieces to something smaller still, it felt natural to suppose that eventually you would reach a final unit, a smallest bit, a point beyond which division no longer made sense. That intuition had a long history behind it. The very old idea of the atom had carried precisely that flavour, a final piece of matter, something indivisible, something that marked the limit, and it is easy to see why that idea was so attractive. It gave the mind a stopping place. It allowed the world to be built from units that were small enough to explain complexity, but not so strange that they threatened the whole enterprise. If matter consisted of atoms, and atoms were the ultimate building blocks, then the universe possessed a kind of basic neatness. There were ingredients, there were combinations, there were rules. It felt orderly, it felt respectable. It felt like the kind of arrangement one could teach without causing anyone to stare moodily into the distance for the rest of the afternoon. By the 19th century, atoms had become more than a philosophical guess. Chemistry had made them useful. Scientists could explain reactions, proportions, and compounds more successfully by treating matter as if it were composed of atoms. The invisible units had become practical tools of reasoning. You could not see them directly, but they helped make sense of what substances did when mixed, heated, cooled, dissolved, or transformed. The atomic picture was earning its keep. Yet at the same time, another line of investigation had been developing, one that had less to do with chemical recipes and more to do with electricity, magnetism, glass tubes, metal plates, and the sort of apparatus that always looks slightly as if it might either reveal a deep truth or explode in a dramatic but educational way. Electricity had been known in various forms for a very long time. People had observed static effects, shocks, sparks, and the dramatic violence of lightning long before they understood what any of it meant. By the time the 19th century was well underway, electricity was no longer just a curiosity. It had become a serious area of study. Scientists were learning how it moved, how it could be generated, how it could interact with magnetism, and how it behaved under different conditions. This was already enough to make the period exciting. But there was a particular class of experiments that began to produce effects so odd and so persistent that the older picture of matter could not stay comfortably intact. These experiments often involved glass tubes from which much of the air had been removed. That detail matters, because a gas at low pressure behaves differently from the dense atmosphere around us. When a high voltage was applied across electrodes inside one of these partially evacuated tubes, strange luminous effects appeared. Glows, beams, patches of light, regions that lit up, and regions that stayed dark. It was the sort of phenomenon that invited both fascination and argument. Was this some form of radiation? Was it a vibration in the ether, which at the time many people still took seriously as a possible medium for light and electromagnetic effects? Was it a stream of particles? Was it something else entirely? The tubes did not come with a little note from nature explaining themselves, so scientists had to infer what was happening by probing the effects from different angles. These glowing tube experiments had an almost theatrical quality to them. In a darkened room, a glass vessel would suddenly reveal sharp lines and eerie fluorescence. A screen inside might light up where something invisible struck it. Objects placed in the path of the effect could cast shadows. Magnets could influence what seemed to be happening. Different experimenters built improved versions of the apparatus, adjusted the pressure, changed the materials, refined the electrical setup, and compared notes with one another across countries and decades. What emerged was not one single dramatic moment in which a curtain rose and an electron stepped forward with perfect timing. It was more like matter becoming increasingly uncomfortable under questioning. At first, what would later be called cathode rays did not announce their true nature in an obvious way. They seemed to emerge from the cathode, the negatively charged electrode, and move across the tube, producing fluorescence where they struck the glass or a prepared screen. That much could be observed. But observation alone did not settle the deeper issue. Were these rays actually rays in the sense of some wave or radiation moving through space? Or were they particles, bits of matter carrying charge? Physicists were divided. Some argued strongly for one interpretation, others preferred another. And because the evidence was difficult and the phenomena occurred under somewhat delicate experimental conditions, the debate had room to grow. It is worth pausing there for a moment, because this is one of those parts of science that often gets cleaned up too much in hindsight. We like neat stories in which old ignorance gives way smoothly to new truth, with everyone nodding appreciatively at the correct moment. Real scientific discovery is often messier. There are competing interpretations, imperfect instruments, strong personalities, partial clues, and theories that seem plausible for a while before being overtaken. The path to the electron was not a tidy march from confusion to clarity. It was a drawn-out negotiation between apparatus and imagination. Nature offered hints. Scientists built better tests. Old concepts strained under new evidence. And gradually, almost reluctantly, matter began to admit that the atom might not be indivisible after all. One of the important clues was that the mysterious effect in these tubes behaved in ways suggestive of a stream coming from the cathode. It travelled in more or less straight lines. It could produce shadows. It could cause certain materials to glow when struck. Under some conditions, its path could be influenced by magnetic fields. That last point was particularly provocative. If the phenomenon responded to magnetism, perhaps it involved something charged. If it involved something charged, perhaps it was not merely an abstract ray, but a movement of matter or some component of matter. Yet this did not immediately settle the issue, because electromagnetic ideas were themselves developing rapidly, and not everyone agreed on what counted as decisive. There is also a broader cultural reason the discovery mattered so much. The atom had functioned not merely as a scientific idea, but as a conceptual endpoint. It was the smallest thing in the picture. To show that the atom had internal parts would be to shift the foundation beneath chemistry and much of physics. It would mean that matter had another layer hidden inside it. It would mean that the final building block was not final. In science, such moments are both thrilling and slightly rude. They do not just add a fact, they rearrange what everyone thought counted as a basic fact. As the experiments improved, the evidence became harder to dismiss. Cathode rays did not behave like an incidental glow. They behaved like something with direction and regularity. Scientists found ways to test whether these rays carried charge and how they responded to electric and magnetic influences. They looked for deflections. They measured how far the paths bent under known conditions. They tried to determine whether the effect depended strongly on the gas in the tube or on the metal used for the electrodes. That issue turned out to be especially revealing. If the mysterious thing varied wildly from one material to another, perhaps it was some local peculiarity of the setup. But if it appeared with the same essential character in many different conditions, then perhaps something universal was being uncovered. That universality was the quiet bombshell. Here was a phenomenon not tied to one special substance, not confined to one odd material, but showing up across many setups as if it belonged to matter in general. That is the sort of clue physicists treasure, because universality hints at something fundamental. A property that appears everywhere is rarely a trivial accident. And as more evidence accumulated, the conclusion became increasingly difficult to avoid. These cathode rays seemed to consist of negatively charged constituents that were much smaller than atoms and common to matter at large. That realization did not simply add another species to the zoo of nature. It shattered the old confidence that atoms were indivisible. Once matter was shown to contain smaller charged ingredients, the atom could no longer be treated as a final uncut block. It had interior structure, it had parts. The philosophical atom and the physical atom parted company. The word remained, but its meaning changed. What had once been imagined as the end of division became instead a kind of middle-level object, built from still deeper ingredients. This was one of those turning points that can seem obvious from the future and astonishing from the inside. From where we stand now, it is almost impossible to imagine learning chemistry or physics without hearing about electrons fairly early on. They are everywhere in the curriculum. They show up in atoms, electricity, bonding, semiconductors, and magnetism. But before their discovery, nature had been doing all of those things without revealing the microscopic carrier. The effects were visible. The agent was not. Then suddenly, through these odd electrical experiments, a hidden ingredient of the world started to come into view. Matter had kept a secret for a very long time, and now it was being cornered by glowing glass and patient measurement. What made the situation even more striking was the scale of the thing being proposed. These constituents were not merely smaller than atoms in some vague poetic sense. They appeared to be dramatically smaller. If atoms were no longer fundamental, then the architecture of matter was deeper than almost anyone had expected. A whole new order of smallness had entered science. This can be difficult to feel in retrospect because modern life has filled our minds with so many tiny scales that another one may not sound especially dramatic. But for scientists at the time, this was an upheaval. The atom had been demoted. A supposedly ultimate unit was now suspected of being composite. And once that door opened, there was no returning to the older innocence. If atoms had parts, what was the arrangement of those parts? How did negative constituents fit into an atom without the whole thing flying apart? What balanced their charge? How were the masses distributed? Why did chemistry still work so well if atoms were internally structured? Every answer seemed to breed fresh questions. This is another mark of a real scientific turning point. It solves one problem and creates a better class of problems in its place. There is a very human side to this as well. Scientists working on these questions were not merely collecting curiosities, they were trying to find a stable picture of reality. They wanted to know what matter was, not just in the practical chemical sense, but in the deeper structural sense. And so each improved measurement, each better tube, each more reliable deflection test was part of a much larger effort to force the world into clearer focus. The electron was not discovered by someone simply peeking harder. It emerged because experimenters learned how to ask nature precise enough questions that vague answers were no longer sufficient. That is one reason the discovery has such enduring charm. It belongs to a period when laboratory apparatus still had a kind of handcrafted intimacy, but the ideas being extracted from it were beginning to reshape the entire foundation of physics. A glowing patch inside a glass tube may not look like the collapse of an old world view, yet that is more or less what it became. The atom, once imagined as the final grain of matter, had been caught harbouring a smaller reality inside itself. Of course, even after the basic conclusion began to settle in, the story was not finished. Knowing that there was a negatively charged constituent smaller than the atom did not immediately tell scientists exactly what it was, how much it weighed, how it fit into atomic structure, or whether all atoms contained it in the same way. There remained the difficult task of characterizing it more fully. Scientists needed numbers. They needed to know the relation between its charge and its mass. They needed to understand whether it was truly universal. They needed to determine how this new ingredient behaved across different experiments. Discovery in science is often less like finding a treasure chest and more like uncovering one corner of a map that then requires years of work to interpret. Still, the mood had changed. Matter had blinked. It had yielded something. The old confidence that atoms were indivisible was no longer secure. This is why the moment feels so important when telling the history slowly. Before the electron could become a textbook object, it first had to become a cracking certainty. Scientists had to realize that the familiar account of matter was incomplete. Only then could they begin building the more intricate picture that would follow. It is also worth noticing that the discovery came not from staring directly at atoms in the way one might inspect grains of dust under better and better lenses. The electron revealed itself indirectly, through effects and inference. That pattern would become deeply characteristic of modern physics. Many of the most important entities in science are not introduced by simple direct sight. They are inferred from tracks, deflections, spectra, energies, and interactions. We come to know them through the marks they leave, and the consistency of the story that emerges from those marks. The electron entered human knowledge through evidence of that kind. It was less a tiny object seen with the eye than a hidden actor whose presence became undeniable because the world kept behaving as though it were there. That, in turn, required a certain maturity in science. One must be willing to trust a well-supported invisible thing over a familiar visible picture. One must let experiment overrule intuition. The intuition said matter should terminate in indivisible atoms. The experiment suggested otherwise, and so intuition had to give way. It is one of the quieter forms of intellectual courage in science. This willingness to say that the world is under no obligation to resemble our first guess. By the closing years of the 19th century, the implications were becoming clear enough that physics could no longer treat the atom as a sealed box. A smaller constituent had been identified, and it was not some rare exception. It appeared to be common to ordinary matter. The world was built from something more intricate than once believed. In a sense, matter had not only given up a secret, it had given up the secret that it had secrets. Once the interior opened at all, the search for deeper structure became a central project of modern physics, and yet even here the electron remained a little evasive. Yes, it seemed smaller than the atom. Yes, it carried negative charge. Yes, it appeared across many substances, but what exactly was it? Was it a fragment chipped off matter in some mechanical way? Was it a universal component present in all atoms? How could such a small thing be measured properly? Could one determine how much charge it carried relative to its mass? Could its path be traced well enough to turn a strange glow into a fully fledged particle of theory and experiment? These were not small matters. They were the next steps in transforming a disturbance in a glass tube into one of the basic entities of modern science. So this period, the moment when matter first surrendered its composure and admitted internal structure, is best understood not as the end of a puzzle, but as the beginning of a sharper one. The old atom had failed to remain indivisible. Something negatively charged had emerged from experiment. A hidden ingredient of nearly everything had stepped partway into view. All that remained was to pin it down with enough precision that nobody could mistake it for a laboratory ghost or an electrical curiosity. And that is where the investigation becomes even more focused, because once scientists realised matter contained something smaller than the atom, the next task was to catch that something clearly enough to measure its character and prove that the world had indeed been harbouring a tiny charged constituent all along. So once scientists had reason to believe that something real was moving through those glowing tubes, the next challenge was no longer just philosophical, it was practical. Suspicion was not enough. A vague sense that matter might contain smaller charged ingredients was exciting, but science cannot live on excitement alone. It needs measurements. It needs a way to turn a strange effect into a definite thing. It needs enough evidence that even a stubborn person with a very serious beard and a strong loyalty to older theories has to pause and admit that something new has been found. That is where the story of the electron becomes especially satisfying, because this is the moment when the hidden agent inside matter stopped being just a curiosity in a glass tube and became something that could be described, compared, and pinned down. One of the central figures in this part of the story was the English physicist Joseph John Thomson, usually referred to as J.J. Thomson. He did not discover electricity itself, and he was not the first person to notice strange rays in discharge tubes. By the time he entered the problem, many experiments had already been done. The mystery was already on the table. Cathode rays had been observed. Their behaviour had been debated. The question was what exactly they were. Thomson's contribution was to push past the argument with a more careful approach, one designed to extract the character of the thing itself rather than merely describe the glowing consequences. That kind of work does not sound glamorous at first. It sounds like the scientific equivalent of being the person who shows up after a dramatic argument and starts calmly checking whether anyone has actually measured anything useful. But this is often how progress happens. A field can spend years circling around a problem until someone finds a cleaner way to ask the question. Thomson did not have the luxury of directly seeing the electron. No one did. He had to infer its existence and properties from how cathode rays behaved under controlled conditions. In other words, he had to trap the invisible through its habits. The apparatus mattered enormously. In these experiments, a glass tube was prepared with very low pressure inside. Electrodes were placed at opposite ends, and a high voltage was applied. Cathode rays emerged from the negative electrode and travelled across the tube. When they struck the glass or a fluorescent screen, they produced a visible glow. That glow was useful because it gave experimenters a way to tell where the rays were going. The rays themselves remained unseen in the ordinary sense, but their impact announced their path. Nature was leaving footprints, and careful people in laboratories were trying to measure the size and shape of the shoe. Earlier work had already suggested that cathode rays travelled in straight lines and could cast shadows. They seemed to come from the cathode and move across the tube in a directed way. There was also evidence that magnets could deflect them. This was a major clue, because moving electric charges are influenced by magnetic fields, but a clue is not the same as a verdict. Some scientists still prefer to think of cathode rays as a kind of wave or disturbance in the ether, rather than a stream of material particles. The debate was not foolish. The late 19th century was full of shifting ideas about light, electricity, magnetism, and the medium through which such effects might propagate. It was not yet obvious how all these concepts would settle. What Thomson needed was a way to show that the rays behaved like charged particles, and to measure something quantitative about them. He studied how the rays were deflected by electric and magnetic fields. If the rays carried charge and had mass, then their path would bend in ways that depended on the relation between those two things. The amount of bending could reveal how much charge they carried, compared with how much inertia they had. This was the key insight. He did not need to weigh a single tiny particle on a microscopic scale. He could infer an important property from motion. That was a beautiful move, and a very modern one. It relied on the idea that if you understand the rules governing motion, then a path through space can tell you what kind of thing is moving, even when you cannot observe it directly. The rays were sent through the tube. Electric and magnetic influences were applied. Their deflection was measured. From this, Thomson calculated the ratio of charge to mass for the particles making up the rays. And what he found was astonishing. The charge-to-mass ratio was far larger than that of any known ion. That meant one of two things. Either these particles carried an enormous charge, much greater than anything expected, or they had a very small mass, far smaller than any atom. The second possibility was the one that made sense, and it was revolutionary. These were not full atoms drifting about. They were much lighter constituents, pieces smaller than atoms themselves. Matter, it seemed, contained something far tinier than the supposedly indivisible atom. The old picture had not merely cracked, it had split open. What made the result even stronger was that the same sort of particles seemed to appear regardless of the material used for the electrodes or the gas left in the tube. That point cannot be overstated. If cathode rays had depended heavily on the specific metal or gas in the apparatus, the effect might have been dismissed as a special quirk of certain substances. But the result kept returning with the same essential character. The particles seemed universal. That implied they were not peculiar to one material. They were common constituents of matter itself. Different substances, when subjected to these conditions, gave rise to the same tiny negatively charged entities. This was not a local accident. It was a general fact about the world. There is something wonderfully unsettling about that moment. Imagine having lived in a time when atoms already seemed small enough and mysterious enough, and then suddenly being told that inside them there exists something much smaller, carrying negative charge, present across ordinary matter and capable of being peeled out in electrical experiments. It would have felt like opening what you thought was a sealed box and discovering an entire hidden mechanism inside. The atom had not been the last word. It had merely been the next level up. Thomson originally used the term corpuscle for these particles. The word electron was already in circulation in related contexts and soon became the standard name, but it is worth remembering that naming often lags slightly behind understanding. Science first has to become convinced that a thing exists. Then it has to decide what to call it without sounding too foolish in the long run. Fortunately, electron turned out to age better than many terms from that era. One can only be grateful that fundamental physics did not settle on something like the tiny electric bit, which would have made every textbook feel slightly less dignified. Still, even after Thomson's result, acceptance was not instant and universal in the simple way school summaries sometimes suggest. Some physicists remained cautious. New results of this magnitude rarely sweep through the scientific world with total smoothness. People worry about experimental error. They wonder whether hidden assumptions are misleading the interpretation. They ask whether an alternative model might explain the data. All of that is healthy. A discovery of this importance should face scrutiny, but the evidence was accumulating in a direction that became increasingly difficult to resist. The particles in cathode rays carried negative charge. They were much lighter than atoms. They appeared across different materials. They were therefore strong candidates for being genuine constituents of matter. This is the point where the phrase first caught begins to feel appropriate. The electron was not caught in the sense of being held in a tiny jar with a label on the side. It was caught in the sense that its behaviour had become measurable enough to identify. Its path could be bent. Its ratio of charge to mass could be inferred. Its universality could be tested. The invisible had been cornered by consistency. Once a phenomenon behaves the same way across many experiments and yields measurable properties, it ceases to be a ghost of the apparatus and becomes an object of physics. It also changed the very meaning of atomic structure. Before this, atoms could still be imagined, at least by many as compact and final units. After Thomson, that was no longer viable. Atoms contain negatively charged components. If atoms as a whole were electrically neutral, then there must also be positive charge somewhere to balance the negative. That raised a fresh question. What was the arrangement inside the atom? How were these electrons embedded in matter? What prevented the structure from collapsing or flying apart? Once again, one answer produced a better puzzle. Thomson proposed an atomic model to deal with this new situation. In his picture, the atom was a kind of diffuse sphere of positive charge with negatively charged electrons embedded within it. Later generations often remember this through a dessert-based analogy, which is memorable but not especially flattering to the atom. The model itself was not absurd at the time. It attempted to reconcile the existence of electrons with the observed neutrality of ordinary matter. If atoms contained negative particles, then the rest of the atom had to provide an equal amount of positive charge. Thomson's idea offered a way to imagine that balance. Of course, that specific atomic model would not survive in the end. Later experiments, especially those involving the scattering of particles from thin metal foils, would force a more dramatic picture in which positive charge was concentrated in a tiny nucleus. But we should not judge too harshly from the future. Thomson had already done something remarkable. He had helped show that atoms were divisible, and that a universal negatively charged constituent existed within them. Even if the full architecture of the atom was still unclear, the old indivisible atom had been decisively replaced by a more layered reality. Another reason this stage matters so much is that it introduced a deeper style of reasoning into physics. The electron was not identified by resemblance to familiar objects. It was identified by abstract but testable properties: charge, mass, response to fields, universality across materials. These are not the features one uses to identify a chair or a loaf of bread. They belong to a more disciplined way of knowing. Modern physics often tells us what something is by telling us how it behaves under a precise set of conditions. That can feel less intuitive than ordinary language, but it is often more reliable. The electron became real to science not because anyone formed a perfect mental picture of it, but because its measurable behaviour fit together into a coherent and repeatable account. And there was another important feature of this discovery that made it especially powerful. The electron did not appear to be fragile or temporary in the way some experimental effects can be. It was stable. It did not depend on a single rare setup. It emerged again and again. That stability mattered because it meant the electron could be treated not as an accidental byproduct of extreme conditions, but as a basic constituent of ordinary matter. The same thing revealed in a vacuum tube belonged to the world outside the tube as well. The laboratory had not manufactured a novelty. It had exposed a resident. Once that realization settled in, physics had to start rethinking everything from the ground up. Chemistry now involved atoms with internal charged parts. Electricity now had a plausible microscopic carrier. Magnetism, conduction, and the behavior of materials acquired a more concrete foundation. The electron became a bridge between large-scale effects and small-scale structure. Sparks and currents and chemical bonds were no longer just broad phenomena to be catalogued. They were connected to the behavior of a specific tiny entity. That is one reason the discovery feels so decisive even now. It linked the tangible world to a newly uncovered microscopic actor. There is a kind of scientific satisfaction in this that is hard to overstate. For centuries, people had observed electrical phenomena without knowing what exactly was moving or shifting at the smallest level. Then, through a combination of experimental patience and conceptual courage, a candidate emerged that could carry the story. Not the whole story, certainly, but a crucial part of it. The electron helped make electricity less mysterious in one sense, even as it made matter more mysterious in another. That exchange is very typical of science. Clarity in one area often reveals deeper strangeness just beneath it. It is also worth taking a moment to appreciate how indirect the entire achievement was. No one opened up an atom with a tiny knife and pointed to the electron sitting inside. The electron was inferred from effects in carefully arranged experiments. That may sound less dramatic than direct sight, but in physics it is often the stronger form of knowledge. Direct appearances can mislead. Measurements under controlled conditions, repeated and interpreted through consistent theory, can reveal structures the eye could never hope to grasp. The electron was first caught not by being seen in a naive way, but by leaving evidence too precise to ignore. Soon other work would strengthen the case further. Additional experiments would measure the electric charge of the electron more directly. Once that charge was known, it became possible to combine it with Thomson ratio and determine the electron mass itself. That would confirm just how extraordinarily light it was compared with atoms. But even before those later refinements, the basic situation had already changed. Matter had been shown to contain a tiny negatively charged component. A major hidden ingredient of the world had stepped into view. For anyone living through that transformation, the emotional effect must have been remarkable. The familiar world had not visibly changed. Tables remained tables, lamps still glowed, metal still conducted, chemistry still behaved in all its practical ways. Yet underneath all that familiarity, the picture of what things were made of had been altered forever. The atom was no longer a final point of rest. It was a structure, a system, a host for smaller constituents. And among those constituents was the electron, newly identified and already indispensable. This was also the beginning of a deeper tension that still follows us now. The electron had become measurable, but that did not mean it had become easy to imagine. Even at this stage, one could say what it did more easily than what it was in the everyday sense. It carried negative charge, it had a very small mass, it responded to electric and magnetic fields, it occurred in all ordinary matter, yet these facts did not automatically produce a comfortable mental picture. Was the electron a tiny hard object, a charged speck, a bit of fluid, some kind of field disturbance? The measurements made it real, but they did not make it intuitively familiar. In a way, the more clearly the electron was caught, the stranger it became. And that is part of what makes this period so important for the larger question we are following tonight. Before this, one might have asked what matter is made of and answered atoms. After Thomson, that answer no longer held. One now had to ask what atoms are made of, and electrons were part of the reply. But then, almost immediately, the next question began to form. If electrons are inside atoms, what are electrons themselves? Are they little pieces of something larger? Are they final units? Are they structured or unstructured? The discovery solved one level of the puzzle and moved the mystery inward by one more step. So the electron was first caught through its effects in cathode ray experiments, then pinned down more sharply through measurements of how those rays bent in electric and magnetic fields, and finally accepted as a universal constituent of matter, because the evidence pointed again and again to the same conclusion. It was an extraordinary achievement, not because it provided a complete final picture, but because it made the hidden interior of matter undeniable. The world could no longer pretend to be made of indivisible atoms. It had yielded a smaller secret, and that secret had charge, almost no mass by comparison, and a talent for changing the whole story wherever it appeared. From there, physics was bound to press further. Once the electron had been identified as something real and common, the next step was to understand how it behaved in a wider range of experiments. And it was there, in the years that followed, that the neatest remaining comforts began to slip away. Because catching the electron was one thing, discovering that it did not behave like an ordinary little particle was something else altogether. For a little while it seemed as though the electron might settle into a fairly understandable role. Strange, yes. Very small, certainly. Important in the electricity and in the structure of matter, absolutely. But still, after its discovery, there was a strong temptation to imagine that physicists had simply added one more tiny object to the inventory of the universe. Matter was no longer made of indivisible atoms. Fine. Atoms contained electrons, also fine. One could picture these electrons as little charged bits, small enough to escape direct sight but still, in spirit, rather like tiny grains or specks. It was not a perfect picture, but it had the comfort of familiarity. Science had uncovered a new particle, Perhaps now the rest would be a matter of careful measurement and improved diagrams. That hope did not last. At first, there were good reasons to keep the particle picture close at hand. Electrons could be emitted from materials. They could be steered by electric and magnetic fields. They could travel from one place to another and strike a screen, producing a visible effect at a definite location. In that sense, they behaved very much as particles ought to behave. If you sent them through an apparatus, they arrived somewhere. If you changed the conditions, their paths changed. If you measured their charge and mass, you could treat them as things moving through space. That was not foolish or naive. It was supported by experiment. The problem was that experiment, having already caused enough trouble by revealing the electron in the first place, was not remotely finished. Part of the difficulty came from the atom itself. Once physicists began building models of atomic structure, they ran into a serious problem. If electrons were simply tiny charged particles moving around inside atoms in the most ordinary classical sense, then trouble followed almost immediately. An electron moving in a curved path would be expected, under the classical ideas of electromagnetism available at the time, to radiate energy. And if it radiated energy continuously, it would lose energy, spiral inward, and collapse into the positively charged part of the atom. In other words, atoms should not remain stable for long. Matter should be alarmingly bad at being matter. That was not a small inconvenience. It was a direct collision between theory and the continued existence of chairs, trees, houses, tea kettles, and listeners lying comfortably under blankets. Atoms clearly were stable. The world was still here. Chemistry still worked. Objects did not dissolve into catastrophe because their electrons had all fallen inward. So something in the classical picture was wrong, or at least incomplete. The electron, when placed inside the atom, was already beginning to behave in ways that ordinary particle intuition could not handle gracefully. There were other clues as well. Light emitted by atoms did not come in a smooth continuous spread of all possible colours. Instead, atoms produced particular spectral lines, sharp and specific. It was as though each kind of atom had a distinct set of allowed notes, rather than a continuous slide up and down a scale. That was very odd if one imagined electrons moving around in arbitrary classical orbits and radiating arbitrarily. Somehow atoms were structured in a much more selective way. They permitted some energy changes and not others. They behaved less like miniature solar systems and more like systems with strict internal rules. Now there were attempts to patch this situation before the full quantum story arrived. One of the most famous came from Niels Bohr, who proposed that electrons in atoms could occupy certain allowed orbits without radiating energy, and that light was emitted or absorbed only when an electron moved from one allowed state to another. This was an ingenious step, and it helped explain features of atomic spectra, especially for hydrogen. But it was also an uneasy compromise. It borrowed some classical imagery and mixed it with new restrictions that did not arise naturally from classical physics. It worked in important ways, but it did not yet provide a fully satisfying account of what an electron really was doing. That is often how revolutions in science begin. Not with a clean replacement of one idea by another, but with a stretch of awkward coexistence. The old picture no longer works, but the new one has not fully arrived. People patch, they improvise, they build half bridges across the conceptual gap and hope the river stays polite. And for a while, that is enough. But the deeper problem remained. Was the electron really a tiny particle following a definite path, only with some mysterious restrictions added on top? Or was the very picture of a particle moving like a little planet around a nucleus leading everyone astray? The first hints that the trouble might be even deeper came from a broader transformation already underway in physics. Light itself had become a source of conceptual embarrassment. For centuries, scientists had argued over whether light was made of particles or waves. By the 19th century, the wave picture had become very powerful. Interference and diffraction made sense in wave terms. Light could spread, overlap, reinforce and cancel in ways that fit the behavior of waves beautifully. Then came the early 20th century, and with it new problems. Certain phenomena, especially the photoelectric effect, suggested that light also behaved in particle-like ways, delivering energy in discrete chunks. So light, which had seemed securely wave-like, was now behaving in a way that required a kind of particulate description as well. That should have been warning enough that nature did not respect the boundaries human intuition preferred, but physics, like the rest of us, sometimes needs to be told the same lesson more than once. If light could act in this dual way, perhaps matter itself might have a similar ambiguity. That was the daring suggestion introduced by Louis de Broglie. He proposed that particles of matter, including electrons, might also have wave-like properties, not just metaphorically, not just in some vague philosophical sense, but physically. Matter might have an associated wavelength. The electron, long treated as a tiny charged particle, might in some circumstances behave like a wave. This was not the sort of proposal that sounded automatically reasonable to people trained on everyday objects. A wave of what, exactly? A wave in what medium? How can a particle be a wave? Those questions came quickly, and fairly enough. But then again, everyday objects do not give us much help here. A tennis ball does not noticeably diffract through a doorway. A loaf of bread does not produce an interference pattern on the kitchen wall, though one suspects modern art would enjoy the result. The wave character of ordinary large objects is so tiny and so thoroughly hidden by their scale and interaction with the environment that common sense never had to account for it. Electrons, however, live on a scale where that excuse stops working. The crucial point was that de Broglie's idea could be tested. If electrons really had wave-like properties, then under the right conditions they should do things waves do. They should show diffraction and interference. They should spread out in ways that no simple little bullet would. That meant the question could move from speculation to experiment. Physics, once again, had a chance to corner the universe with apparatus. One of the landmark demonstrations came from the work of Clinton Davison and Lester Germer in the United States. They were studying how electrons scattered from a crystal of nickel. The original goal was not necessarily to prove grand philosophical claims about the nature of matter. Science often proceeds in this pleasantly indirect way, where people investigating one thing stumble into evidence for something much larger. What they found was that electrons scattered in a pattern that made sense if they were behaving like waves. The crystal, with its regular arrangement of atoms, acted in effect like a structure capable of producing diffraction. The electrons did not simply bounce off as tiny hard pellets. They produced an organised pattern characteristic of wave behaviour. Around the same time, George Paget Thomson, the son of J.J. Thomson, also performed experiments that showed electron diffraction. There is something almost too perfect about that historical detail. The father had helped establish the electron as a particle. The son helped demonstrate its wave-like nature. One cannot help feeling that the universe was indulging in a bit of theatrical symmetry. It is the sort of story a novelist might be advised to tone down for fear of seeming implausible. Yet physics sometimes arranges these things without consulting anyone about subtlety. The experimental results were difficult to deny. Electrons could produce interference and diffraction patterns. Those are not the natural habits of tiny classical particles moving independently along fixed little tracks. They are behaviours associated with waves, and so the electron stopped fitting comfortably into the category people had first assigned to it. It was not enough to say the electron is a particle and leave it there. The wave behaviour was real, measurable, and essential. This was not merely a decorative complication. It changed the meaning of what one could say about the electron at all. In classical thinking, a particle has a position and a path. It goes from here to there. If you know enough about its starting conditions and the forces acting on it, you can in principle trace its motion. That is the old dream. But wave behaviour disrupts that picture. A wave is spread out. It can pass through more than one opening. It can interfere with itself. It does not live in one place in the neat little way a particle does. So if the electron shows genuine wave properties, then what exactly is travelling when an electron moves? Is the electron spread out? Is it smeared through space? Does it choose a path only when measured? Does it take multiple possible routes at once? The ordinary language starts to come apart very quickly. This became especially vivid in the context of the double-slit experiment, even though one has to be careful not to reduce the whole mystery to a single classroom favourite. The setup is conceptually simple and physically devastating. If you send ordinary particles through two narrow openings, you expect them to go through one slit or the other and produce two corresponding bands on a screen behind. If you send waves through two slits, you expect them to spread out, overlap, and create an interference pattern with regions of reinforcement and cancellation. When electrons are sent through such a setup under suitable conditions, they produce an interference pattern. Even more unsettling, they do so even when sent one at a time. Each electron arrives as a localized event on the screen, like a particle, but the overall pattern builds up as though each electron had behaved like a wave capable of interfering. That result has made generations of students and physicists stare at diagrams in varying states of disbelief. One electron at a time, localized arrivals, yet a pattern requiring wave-like behavior. If one insists on asking through which slit the electron really went in the old classical sense, trouble follows. If one arranges the experiment to determine the path more explicitly, the interference pattern is destroyed. It is as though the electron refuses to give us both a definite classical trajectory and a wave interference pattern at the same time. The universe seems to say you may ask certain questions together, but not all of them in the way you would prefer. By this stage, saying that the electron stopped behaving like a particle is not quite the whole truth, though it captures the shock people felt. The electron did not cease to produce particle-like effects. It still arrived at definite locations when detected. It still transferred charge in discrete amounts. It still behaved in many settings as a countable entity. What changed was that the particle description alone no longer sufficed. The electron had to be described in a way that retained both aspects without collapsing into nonsense, and that was the challenge that helped drive the development of quantum mechanics. The emerging quantum picture did not say that the electron is secretly a classical wave after all, and everyone had simply been too harsh on ripples. Nor did it say that the electron is secretly a classical particle with some odd decorative tricks. It said, in effect, that both classical categories are incomplete. The electron is a quantum object. It shows particle-like and wave-like features depending on how it is described and how it is measured, but neither old category fully contains it. This is less comforting than it sounds. Human beings like being able to say what something is in one clean sentence. The quantum world prefers to offer a mathematically powerful account that leaves ordinary intuition feeling a little underdressed. Part of what made this so hard to absorb is that the word wave itself carries baggage from everyday life. We think of water waves, sound waves, ripples on a pond, the sort of thing that clearly involves a medium waving around. But the wave associated with an electron is not best pictured as a little wobble in some familiar substance. In quantum theory, the wave description is tied to a mathematical object that encodes the probabilities of finding the electron in different places under different conditions. This is already moving toward the next stage of the story, where the electron inside the atom stops resembling a tiny planet and starts being described as a cloud of possibilities. But even before we get there, the essential point is that the electron can no longer be imagined as a small hard pellet flying neatly through space with a single hidden path. We simply have not measured well enough yet. The discomfort deepened further with Werner Heisenberg's work on uncertainty. Again, one has to tread carefully, because this idea is often explained in ways that make it sound like a flaw in our measuring tools, or a polite request for lower expectations. It is more profound than that. In quantum mechanics, certain pairs of properties cannot both be specified with arbitrary precision in the same state. This is not merely a practical inconvenience caused by clumsy experimenters poking delicate objects. It reflects the structure of the theory itself. For the electron, that means the old dream of a sharply defined position and momentum existing together as hidden classical facts becomes deeply problematic. In ordinary life, that sounds absurd. Surely a thing is where it is and moving how it is moving, whether or not we know it. But the electron does not owe us obedience to ordinary life. Quantum mechanics does not simply withhold information we might someday retrieve with better technique. It changes what it means to speak of the electron state in the first place. The more tightly one tries to pin down the electron location, the less tidy its momentum description becomes, and vice versa. Classical particle language survives only in limited and approximate ways. There was resistance to all of this, as one would expect. Not everyone welcomed a theory that worked beautifully while undermining old habits of thought. Even some of the founders of quantum theory were uneasy about what it seemed to imply. The mathematics could predict outcomes with extraordinary success, but the interpretation remained philosophically unsettling. What is the electron doing between measurements? Is the wave description a physical reality, or merely a tool for calculating outcomes? Does the electron have definite properties before measurement, or only probabilities? These questions spilled beyond laboratory procedure into debates about the meaning of physical reality itself, and yet, practical success kept strengthening the quantum view. It explained atomic structure far better than classical models could. It accounted for spectra, bonding, and the stability of matter. It made sense of why electrons in atoms do not simply spiral into the nucleus. It described the allowed states in which electrons can exist, and the patterns those states produce. In other words, the theory did not merely rescue a few awkward experiments, it rebuilt the foundations of atomic physics. The electron had forced a conceptual revolution because the world simply behaved as though the revolution were true. There is something almost mischievous about the electron in this period of science. First, it reveals that atoms are not indivisible. Then, just as physicists begin treating it as a newly discovered tiny particle, it begins producing wave-like effects and refuses to sit still inside classical categories. It is as though, every time the human mind reaches for a manageable picture, the electron slips one step sideways and leaves that picture looking embarrassingly literal. At the same time, this was not chaos. It is important to keep that in view. The electron did not become unknowable in the sense of being beyond science. Quite the opposite. Quantum mechanics made electron behavior more accurately describable than ever before. The problem was not lack of prediction. The problem was that the predictions came wrapped in concepts unfamiliar to common sense. The electron had not become vague. It had become precise in a way that challenged the older language of little objects moving along hidden paths. And so the shift was not from knowledge to mystery, but from one kind of understanding to another. The earlier understanding asked us to imagine the electron as a particle, in the ordinary mechanical sense. The newer understanding asked us to accept that the electron is represented by a quantum state, exhibits wave behavior, yields localized outcomes when measured, and resists any simple translation back into everyday imagery. It was richer, more powerful, and less comfortable. This change had enormous consequences for how one thinks about the atom. If electrons are not little planets circling in definite tracks, then the old atomic diagrams taught in their simplest form are only rough stepping stones. The real story is not about tiny bodies orbiting like moons around a central lump. It is about quantized states, probabilities, spatial distributions, and rules that determine how electrons can occupy the atom. The failure of the purely particulate picture opened the way to a much stranger but more accurate description. That is where the narrative naturally begins to turn next. Once physicists accepted that the electron could not be treated as an ordinary particle with a well-defined miniature orbit, they needed a new way to picture its presence around the nucleus. And that new way was not a tidy mechanical model. It was something more like a patterned cloud, not a fog of uncertainty because science had become lazy, but a real reflection of the way the electron is distributed and described in the quantum world. The atom, which had already lost its simplicity once, was about to become stranger in a quieter and more beautiful way. By the time physicists had accepted that the electron could not be treated as an ordinary little particle, moving around inside the atom like a bead on a hidden wire, they faced a new problem that was both scientific and psychological. The scientific problem was how to describe what the electron was actually doing. The psychological problem was that the replacement picture was much harder to draw on a classroom board without making everyone quietly miss the old one. A little planet circling a central sun may have been wrong, but it had one enormous advantage. It was easy to imagine. You could point to it. You could sketch it in a few seconds. You could say there is the nucleus, and there is the electron going around it. And although that picture began causing trouble the moment anyone asked serious questions, it still gave the mind something to hold. The quantum picture took that comfortable little model away and replaced it with something more accurate but far less cooperative. What replaced it was not emptiness, and not a confession of ignorance in the lazy sense. It was not that physicists looked at the atom, gave up, and said perhaps the electron is somewhere in the general vicinity, and that will have to do. The new picture was far more precise than that. It was simply precise in a way that no longer matched everyday intuitions about tiny objects following tiny paths. The electron in an atom is described by a quantum state, and that state tells us about the possible outcomes of measurements. It tells us where the electron is likely to be found if we look for it. It tells us which energies are allowed. It tells us how the electron relates to the nucleus and to other electrons. What it does not give us in the old classical way is a neat little orbit like a miniature planet tracing circles or ellipses in space. That is where the idea of the quantum cloud enters. The word cloud can be a little misleading if taken too casually, because it makes the electron sound like a vague puff of smoke drifting around the nucleus in a whimsical state of indecision. That is not really the point. A quantum cloud is not a random haze. It is a structured distribution. It is a way of representing where the electron is more likely or less likely to be found. If one measures the electron position many times in identically prepared atoms, the results do not fill space evenly, and they do not fall along a classical orbit. Instead, they build up a pattern. Dense regions correspond to greater likelihood. Sparse regions correspond to lesser likelihood. In that sense, the cloud is not a literal fluffy substance. It is a map of probability tied to the electron quantum state. This change in picture was one of the great conceptual shifts in all of science, because it required people to stop asking the atom for the wrong kind of image. Classical intuition wanted a path. It wanted the electron to be somewhere definite at every instant, gliding around in a tidy route, preferably with arrows to show direction and speed. The quantum atom refused to provide that comfort. It offered standing patterns instead of tracks. It offered allowed states rather than arbitrary motion. It offered probability distributions rather than little planetary journeys. And the more closely experiments agreed with this strange description, the harder it became to pretend that the old picture was merely incomplete in some minor way. It had to be replaced at the foundation. A useful way to feel the logic of this is to think about waves in a confined space. If you pluck a string on a musical instrument, the string does not vibrate in just any shape at all. Only certain standing patterns fit properly between the fixed ends. The allowed vibrations have structure. Some are simpler, some more complicated, but not every imaginable pattern is possible. Something a bit like that lies behind the quantum description of the electron in the atom. The electron is not a tiny string, and the atom is not a violin, so one must not lean too hard on the analogy. But the essential idea is helpful. Inside the atom, the electron is described by a wave-like quantum state, and only certain stable patterns are allowed around the nucleus. Those allowed patterns correspond to specific energies and spatial distributions. The atom is not a place where the electron may do absolutely anything. It is a place where the rules permit some arrangements and forbid others. That's why atoms have distinct spectra. When an electron changes from one allowed state to another, the atom absorbs or emits specific amounts of energy, rather than any amount at all. The old planetary picture had struggled to explain this cleanly. The quantum cloud picture makes it natural. The atom has a set of quantized possibilities built into it. The electron occupies one of them. If it changes state, the change is specific, not arbitrary. The atom behaves less like a tiny solar system and more like a tightly regulated structure with a very strong opinion about what is permitted. And this is where the cloud becomes not just strange but deeply practical. The chemistry of the world depends on these allowed electron states. The way atoms bond, the way molecules form, the way materials conduct or resist electricity, the way certain substances absorb light and others reflect it. All of this depends on the arrangement of electrons in these quantum states. So when physicists abandoned the old orbit picture, they were not stepping into decorative philosophical weirdness. They were moving toward the framework that actually explains why matter behaves the way it does. The cloud may be harder to picture, but it is the cloud that gives us chemistry, not the little planet. One can understand why the older image survived so stubbornly in popular imagination. It flatters common sense. It lets the atom feel like a smaller version of the familiar world. We already know planets and moons. We already understand things going around other things. The trouble is that this image smuggles in classical expectations that are simply not true at atomic scales. A planet can in principle have a reasonably definite position and velocity at each moment. A classical orbit is a trajectory through time. An electron in an atom is not best thought of that way. If you insist on imagining it as a tiny object hidden somewhere on a track, you will begin asking questions that the actual theory does not support in the form you mean them. Which point of the orbit is it at right now? How fast is it going along the path? Why does it not radiate and spiral inward? The quantum description dissolves these questions not by refusing to answer them out of spite, but by showing that the picture behind the questions was already wrong. Instead of tracks, we get orbitals. That word is unfortunately similar enough to orbit to cause endless confusion, which feels like a small act of cruelty on the part of scientific terminology. An orbital is not an orbit. It is a quantum state for the electron in the atom, with a characteristic spatial pattern. Some orbitals are more compact and symmetrical. Others have more elaborate shapes, with regions where the electron is likely to be found separated by regions where it is not. These are not little roads in space. They are patterns in the probability distribution associated with the electron state. If you have ever seen textbook pictures of these orbitals, they often look like smooth blobs or lobes around a central nucleus. Again, the temptation is to think of them as places where the electron is physically smeared like jam across toast. That is not quite right either. The pictures are telling you about the structure of the state and the likelihood of detection in different regions. If you repeat measurements across many identical atoms, the outcomes accumulate into those patterns. So the orbital is neither a classical path nor a literal goo. It is a highly organized quantum description of where the electron can show up. This matters because the shapes of these orbitals are not decorative side details. They help determine how atoms interact with one another. Some electron states reach outward in ways that make bonding easier. Some are more tightly held near the nucleus. Some can overlap with states in neighbouring atoms to form molecular bonds. Others influence magnetic behaviour or the geometry of molecules. The cloud picture, strange as it sounds at first, turns out to be exactly what the visible world requires. The shape of a molecule, the strength of a bond, the difference between one material and another, all depend on the fact that electrons occupy structured quantum states rather than tiny classical orbits. There is also a deeper reason the cloud picture is more than a compromise. In quantum mechanics, the wave description is not an optional artistic overlay, placed on top of a particle that is really doing something simpler behind the scenes. The wave structure is central to the way the electron behaves. It is why interference happens. It is why only certain states are allowed in atoms. It is why the position of an electron is not a hidden classical fact, waiting patiently for us to uncover without disturbing anything else. The electron is not merely difficult to track because it is too small and quick. It belongs to a different kind of description altogether. That can feel frustrating, because human thought likes objects with edges. We like to know where things begin and end. A chair occupies space. A spoon occupies space. Even a grain of dust has location and a shape in the ordinary sense. The electron asks us to loosen that instinct. In an atom, it is not best thought of as a tiny object with a sharp little boundary and a private itinerary. It is better understood through the mathematical pattern that governs its possible appearances. The cloud, in this sense, is what an electron in an atom looks like when reality is being honest, and common sense is being slightly overruled. None of this means the electron ceases to be real. Quite the opposite. One of the most important habits to resist when discussing quantum ideas is the drift into language that makes everything sound vague or dreamlike. The quantum atom is not blurry because science is weak there. It is structured in a way that forces us to use probability and quantum states. Those are not signs of defeat. They are the correct language for what experiments reveal. A hydrogen atom has a ground state that can be described with extraordinary accuracy. The cloud associated with that state is not a guess. It is part of a predictive framework that works with astonishing precision. The cloud picture also explains why the atom does not collapse in on itself. Under the old classical expectations, an electron circling a nucleus should behave like an accelerating charge and continuously radiate energy, spiraling inward. But the quantum electron in a stable atomic state is not following a classical orbit at all. It occupies an allowed state. There is no continuous inward collapse because the theory does not describe the electron as a little planet bleeding energy as it loops around the nucleus. The stability of matter, which had looked impossible under classical assumptions, becomes natural once the electron is understood as occupying quantized states. This is a very important point because it reminds us that the strange picture is not just strange for the sake of being strange. It solves real problems. It tells us why atoms exist in stable forms. It tells us why they have characteristic sizes. It tells us why they emit and absorb light in discrete patterns. It tells us why chemistry works. Often the best sign that a scientific idea is on the right track is not that it feels comfortable, but that it makes many previously disconnected facts line up at once. The quantum cloud did exactly that. One of the more quietly remarkable consequences of this picture is that most of what we think of as the shape and behaviour of matter comes not from hard little surfaces touching in a classical way, but from these structured electron states. The size of an atom is largely about the spread of its electron cloud. The ways atoms fit together into molecules depend on how those clouds combine or repel. Even the apparent firmness of matter has deep roots in the quantum rules governing electrons, so the cloud is not a mere abstract correction to a simpler story. It is the part of the story that actually gives matter its everyday character. There is a temptation at this point to ask whether the cloud means the electron is literally everywhere in the cloud at once until measured. That is one of those questions that sounds simple and then begins to splinter the moment one handles it too confidently. Different interpretations of quantum mechanics answer in different tones. Some emphasize the wave function as a real physical object. Others treat it more cautiously as a tool for assigning probabilities to outcomes. What nearly everyone agrees on is the practical core. Before measurement, the electron is described by a quantum state that can be spread out over space. After a position measurement, one obtains a localized result. The cloud tells you how those localized outcomes are distributed when the system is prepared in the same way again and again. For the purposes of understanding atoms, that practical core already takes us very far. You do not need to settle every philosophical dispute about quantum reality in order to understand why the old planetary model fails. The electron in an atom is not circling along a little hidden road. It occupies a state with a definite energy and a characteristic spatial pattern. That is the modern picture, and it works. The fact that it leaves us still arguing over what kind of reality a quantum state has is part of the enduring charm and irritation of physics. Another reason the cloud image is so powerful is that it helps us see why not all electrons in an atom can just pile into the same arrangement. The quantum states available around a nucleus have a certain organised structure to them, and electrons must occupy them according to strict rules. These rules help build the architecture of the periodic table. They determine why the elements repeat in families and why chemical behaviour changes in patterns rather than randomly. Without the cloud picture and the rules attached to it, chemistry would be a mess of disconnected facts. With it, the periodic table becomes a map of electron arrangements. The visible order of the elements comes from the invisible order of the quantum states. That point is easy to miss because the periodic table often gets presented as though it simply exists in its own right, a kind of great wall chart humanity found in a cave and decided to laminate. In truth, its structure reflects the way electrons occupy allowed states around nuclei. The rows and columns are not arbitrary. They emerge from the quantum architecture of electrons in atoms. So even something as familiar as the repeating behaviour of elements owes its existence to the fact that electrons are not tiny planets, but occupants of orbitals. And the more electrons an atom has, the richer and more crowded this picture becomes. In hydrogen, with only one electron, the basic structure is already revealing. In larger atoms, multiple electrons interact, and the arrangement of their clouds becomes more complex. Yet the same basic lesson remains. The atom is not a miniature solar system with a swarm of tiny planets on fixed tracks. It is a quantum system with allowed states, spatial patterns, and deep rules about occupancy and interaction. The cloud is not a fallback image for when the real one is too hard. It is the real one, at least insofar as any image can represent the mathematics honestly enough to guide thought. It is also worth noticing that this picture brings with it a different style of humility. In the classical world, one could imagine that if only the instruments were perfect enough, the hidden path of the electron would be revealed exactly as a small object going around the nucleus. The quantum picture tells us that this hope is not just technologically ambitious, but conceptually misplaced. The atom is not waiting behind a curtain to become classical once our microscopes are sufficiently nosy. Its structure is genuinely quantum. That is what it is. The cloud is not a blur caused by poor resolution. It is a faithful reflection of the kind of object we're dealing with. This shift in attitude took time to absorb. It still takes time to absorb. Even now, many people retain some half-remembered image of electrons orbiting nuclei because it feels simpler. And one can be kind about that. Early learning often needs stepping stones. The danger comes only when the stepping stone gets mistaken for the destination. The real atomic picture is less intuitive, but it is also more satisfying once it settles in. It explains more. It aligns with experiment. It shows why matter is stable, why chemistry has structure, and why electrons can neither be reduced to tiny planets, nor dissolved into pure vagueness. If anything, the quantum cloud makes the electron more interesting than the old picture ever could. A tiny planet is merely a small version of something we already know. A structured quantum state is genuinely new. It tells us that nature, at its deeper levels, is not simply the familiar world made smaller. It has its own logic. The electron in an atom is one of the clearest places where that logic reveals itself. It is not following a path. It is inhabiting a possibility structure, a pattern of allowed presence shaped by the laws of quantum mechanics and the pull of the nucleus. And once that becomes clear, another question naturally starts pressing forward. If the electron is not a miniature planet and not a little bead tracing a route, then what features does it actually carry with it into this quantum world? It has charge, certainly. It has mass. But it also has other built-in habits that matter enormously. It responds to magnetic fields in a particular way. It has an intrinsic kind of angular character that is not the same as a tiny ball literally spinning through space, however tempting that phrase may be. It obeys strict rules about how it can share states with other electrons. In other words, once the cloud picture replaces the old orbit picture, the electron starts to look less like a little object and more like a fundamental quantum entity with a very specific set of built-in traits. And those traits are the next part of what makes the electron so strange and so central to the way the world holds together. Once the picture of the electron as a tiny planet has been set aside, The next sensible thing to ask is what the electron actually brings with it into the world. If it is not best understood as a little bead running laps around a nucleus, then what sort of entity is it? What fixed traits does it have? What makes one electron behave like every other electron? And why do those traits matter so much for the structure of matter, for chemistry, for electricity, for magnetism, and for the strange rules that keep the material world from becoming complete nonsense? This is where the electron starts to seem less like a miniature object and more like a bundle of built-in physical habits that nature takes very seriously. Some of those habits are familiar by name, even to people who have not spent much time with physics. Charge is one, spin is another, though spin is famous for sounding as though it should be simple and then immediately becoming less simple the moment anyone explains it. Then there are other features that matter just as much, even if they do not always get top billing in popular descriptions. The electron has mass, though very little by everyday standards. It belongs to a certain family of particles. It obeys rules that stop identical electrons from all collapsing into the same state. It interacts in some ways and not in others. It has a stubborn sameness wherever it appears. These are not decorative details. They are the reason the electron can help build atoms, conduct electricity, shape the periodic table, and give matter many of its visible and invisible behaviors. Let us begin with charge, because charge is in some ways the most obvious odd habit of the electron. The electron carries negative electric charge. That sounds tidy enough at first. We say it in school, we write it in notes. It becomes one of those scientific facts that feel settled very quickly, perhaps too quickly. But electric charge is a very deep property. It is not just a label attached to the electron like a luggage tag. It is a built-in feature of how the electron behaves in the presence of electric and magnetic fields, and how it interacts with other charged things. The electron is not neutral and then persuaded to act charged under special circumstances. Being charged is part of what it is. That charge is why electrons respond to electric fields. It is why they can be pushed and guided in circuits. It is why oppositely charged particles attract and like charges repel. It is why electrons can be bound to positively charged nuclei in atoms. Without electric charge, the whole architecture of atomic matter would fail immediately. There would be no familiar atoms in the ordinary sense, because the negatively charged electrons would not be held in structured relation to the positive charge in the nucleus. Chemistry would disappear before it had begun. Materials would lose the electromagnetic relationships that help define their structure. Life, technology, and the reassuring existence of tables would all become much less likely. It is also important that the electron charge always comes in the same amount. One electron is not slightly more negative than another because it woke up in a mood. The charge is fixed and universal. This is one of the great regularities of nature. Electrons are identical not just in some broad family resemblance sense, but in this very exact way. The electron in your body and the electron in a metal wire and the electron in a distant star carry the same amount of charge. Physics depends on that sameness. If electron charge wandered casually from one example to the next, matter would not behave with the consistency required for chemistry, for stable atoms, or for the general predictability on which the universe has rather heavily relied. There is another very useful consequence of this fixed charge. It helps explain why electric charge in ordinary situations often appears in discrete steps. The electron became one of the clearest examples that the microscopic world does not always vary smoothly in every respect. Charge has a kind of granularity to it in matter. You do not usually encounter a random arbitrary sliver of electron charge wandering through the kitchen. Instead, the electron carries its characteristic amount, and other charged particles carry their own fixed amounts. Nature, at least in the matter we ordinarily deal with, seems to build electric behavior out of these definite units, rather than an endless continuum. That fact became especially important when later experiments pinned down the electron charge more directly and showed just how fundamental that unit is. Of course, charge alone does not tell the whole story. a particle with charge could still, in principle, be something rather ordinary in its behaviour if it did not come with other built-in traits that complicate the picture. But the electron does. The next famous one is spin, and here language begins one of its little betrayals. Spin sounds as though it should mean the electron is literally spinning around like a tiny top. This image is tempting because it gives the mind something mechanical to hold. One imagines a minuscule charged sphere rotating on an axis, perhaps with all the confidence of a toy gyroscope. The trouble is that this classical picture does not actually work. The electron is not best understood as a little ball, physically rotating in ordinary space in the familiar sense. So why call it spin at all? Because when physicists first encountered the need for this property, it behaved in some ways rather like intrinsic angular momentum. It contributed to magnetic behaviour. It helped explain fine details in atomic structure and spectra. It acted as though the electron carried an internal angular character that could not be reduced to ordinary orbital motion around the nucleus. The word spin survived because it was useful and memorable, but it is one of those scientific terms that must be handled with care. The electron is spin, yes, but not because it is literally a tiny planet spinning on its own axis in the way a classical object would. What matters physically is that spin is intrinsic. The electron has it as part of its nature. You do not give the electron spin by making it move around something else. You do not wind it up. You do not set it twirling. An electron at rest relative to some frame still has this property. It is built in. That is a very important difference from ordinary angular momentum in daily life. A bicycle wheel has angular momentum because it is turning. A planet has angular momentum because it is moving in its orbit and rotating on its axis. The electron spin is not that sort of acquired motion. It is a quantum property the electron simply possesses. This intrinsic spin has consequences that are anything but minor. One of the biggest is magnetic behaviour. Because the electron carries charge and also has spin, it behaves like a tiny magnetic entity in a way that affects atoms and materials profoundly. This is part of why magnetism in matter is so deeply tied to electron arrangement. In many materials, the magnetic behaviour depends on how electron spins line up or cancel out. In some substances, spins pair off in ways that reduce large-scale magnetism. In others, enough alignment occurs to create a stronger magnetic effect. So the electron, once again, turns out not to be a side character. Its built-in traits help determine whether a material responds weakly or strongly to magnetic fields, or becomes a magnet at all. Spin also matters because it comes with strict quantum rules. Electrons are not free to pile into atomic states however they like. Identical electrons must obey what is known as the exclusion principle, associated most famously with Wolfgang Pauli. The principle says, in effect, that electrons cannot all occupy the exact same quantum state in an atom. This is one of the deepest ordering rules in nature. It is not merely a suggestion or a statistical tendency. It is one of the reasons matter has structure instead of collapsing into a dull uniform heap. To feel how important that is, consider what atoms would be like if electrons had no such restriction. They could all simply sink into the lowest available state around the nucleus. The rich layered structure of electron arrangements would vanish. Chemistry as we know it would collapse along with the periodic table. Elements would not display the same repeating patterns. Matter would not organize into the familiar variety of substances and bonds. The exclusion principle is one of those rules that sounds technical until you realize it is doing a vast amount of hidden labor. It helps create the architecture of atoms, and through that the architecture of the material world. This is where spin stops being a strange extra detail and becomes one of the reasons your world has texture. Because electrons come with spin, and because that spin enters the rules governing which states electrons may share, atoms fill their available states in a structured way, rather than all at once into the same lowest option. That filling pattern is what underlies the periodic table. It shapes how many outer electrons an atom has available for bonding. It influences chemical behaviour from one element to the next. In that sense, the periodic table is not just a list of substances. It is a map of how electrons, with their charge and spin and quantum rules, arrange themselves around nuclei. There is also a broader class of odd habits that comes from the fact that electrons belong to a category of particles known as fermions. That label may sound like the name of a mildly disappointed 19th century landowner, but in physics it signals something very specific. Fermions obey a particular statistical behaviour. They are the sort of quantum entities that respect the exclusion principle. Electrons, protons, neutrons, quarks, and a few others fall into this family. Photons do not. This difference matters enormously, because the collective behaviour of fermions is unlike the collective behaviour of particles that are happy to gather in the same state in large numbers. What this means for the electron is that it naturally contributes to layered structures and occupancy rules, rather than mass crowding into a single condition. In atoms, electrons fill states one by one in an organised sequence. In solids, this fermion character influences how electrons populate energy levels, and how materials behave as conductors, insulators, or semiconductors. In dense stars, the same basic exclusion effect contributes to the pressure that helps resist further collapse. So a property that might look at first like a technical rule from a quantum mechanics lecture turns out to have consequences that reach from household materials to the structure of stars. The electron also has mass, though compared with protons and neutrons it is much lighter. That may sound like a plain bookkeeping fact, but it matters a great deal. Because electrons are light, they can be moved and accelerated more easily than the much heavier particles in atomic nuclei. That is one reason they play the starring role in electricity and in many dynamic processes inside atoms and materials. The nucleus contains most of the atom mass, but the electrons do much of the visible chemical and electrical work. They are the lighter, more mobile part of the atomic arrangement. In a way, the heavy nucleus provides the central positive anchor, while the electrons provide much of the flexibility and interaction that gives matter its behaviour. It is worth noting that the electron mass is also intrinsic. Like its charge and spin, it is not something the electron borrows from circumstances in the ordinary sense. Wherever you find an electron, you find that same mass. This sameness is part of the remarkable reliability of the particle. Nature does not offer a menu of slightly different electron models with optional upgrades. The electron is stable in its basic identity. That is one reason theories involving electrons can work across such a wide range of scales and systems. The same particle in a hydrogen atom, in a metal, in a vacuum beam, or in a biological molecule is still the same electron. Then there is the question of how the electron interacts. The electron feels the electromagnetic interaction because it has charge. It also participates in the weak interaction, though that is less visible in everyday chemistry and electricity. It does not participate in the strong interaction, the one that binds quarks into protons and neutrons and helps hold atomic nuclei together. That difference matters because it helps separate the electron from the particles that live inside the nucleus in a more intimate way. Quarks are tied to the strong interaction. Electrons are not. So even before we ask what the electron is made of, its interaction pattern already sets it apart from some of the other building blocks of matter. This can sound abstract, but there is a practical point hiding inside it. The electron is not just defined by shape or size, if such classical notions even apply cleanly. It is defined by the package of properties and interactions it carries. Charge, mass, spin, the family it belongs to, the rules it obeys, the interactions it responds to. This is increasingly how modern physics identifies a particle, not by tiny visual appearance, but by its role in the network of laws. In that sense, the electron is less like a little object with a surface, and more like a stable entry in nature list of allowed entities. There is another odd habit worth mentioning, because it can sound almost trivial at first, and then become strangely profound. Electrons are identical in a way ordinary objects are not. If you own two spoons, you can tell them apart by scratches, shape, weight, or the suspicious bend in the cheaper one. Two electrons do not come with such individuality. They are not merely very similar, they are indistinguishable in the strong physical sense that swapping one for another does not create a new physical situation of the ordinary kind. Quantum theory takes that indistinguishability seriously. It is part of why electron statistics and exclusion work the way they do. This is another place where the small-scale world quietly departs from everyday common sense. The universe is not keeping separate little biographies for each electron. That indistinguishability contributes to the collective order of matter. Because electrons are identical fermions, their arrangements in atoms and solids are governed by very strict patterns. This influences why materials have the electronic structures they do, why some are metallic and others insulating, why chemical bonds form in certain ways, and why the periodic table repeats. The sameness of electrons is not a boring detail. It is one of the foundations of order in the material world. There is also the matter of stability. The electron appears to be stable, at least on timescales far beyond anything relevant to ordinary experience and current experiment. It does not spontaneously fall apart in the way many unstable particles do. This is a very fortunate habit. If electrons were casually decaying into other things, atoms would be in constant trouble, and the universe would have a much harder time sustaining long-lived structures. Stability is easy to take for granted because our whole existence depends on countless stable ingredients behaving themselves long enough for life and stars and chemistry to happen. The electron is one of those ingredients, quietly dependable, almost annoyingly fundamental, and yet, for all this dependability, the electron remains conceptually slippery because these properties do not stack into a simple classical picture. Charge is not like colour. Spin is not literal spinning. Mass is not evidence of a tiny hard lump in the ordinary sense. Magnetic behaviour emerges from quantum traits that do not map neatly onto little turning gears. Exclusion is not a tiny elbowing motion by which electrons physically shove one another away from a seat in the atom. The whole package resists cartoon treatment. Each property is real and measurable, but their combination points toward a kind of entity that belongs fully to quantum theory, rather than to ordinary visual imagination. That is often the deeper lesson of the electron. Every time you think you're about to make it fully familiar, one of its properties refuses to cooperate with the image. Charge makes it central to electricity and atomic structure, but charge itself is a primitive property rather than a thing explained in household terms. Spin sounds mechanical, and then turns out not to be mechanical in the old way. The exclusion principle sounds like crowd control, and turns out to be woven into the statistics of identical quantum particles. Even mass, the most ordinary sounding trait of all, does not simply turn the electron into a tiny pebble that could be held in a small enough pair of fingers if only one had better equipment. Still, physics does not treat this as failure. The electron may resist ordinary pictures, but it rewards precise description. Its charge can be measured. Its spin effects can be observed. Its role in atomic spectra, magnetism, and chemistry can be calculated with extraordinary accuracy. Its identical nature is part of a theory that predicts a huge range of phenomena correctly. So while the electron is strange, it is not vague. This distinction matters. Strange in physics often means the world is asking us to learn better categories, not that the world has become blurry or mystical. And the more you think about these built-in habits, the more they push the larger question back into view. If the electron carries charge as a fixed intrinsic property, if it has spin as a built-in quantum trait, if it belongs to a family of identical fermions obeying strict rules, then what exactly is the electron underneath all that? Is charge a sign of internal structure? Is spin evidence that there is something turning or circulating inside it? Is the electron made of smaller pieces whose combined motion produces these traits? Or are charge and spin simply fundamental features of a particle that is not built from anything smaller at all? This is where curiosity becomes especially difficult to satisfy, because the habits of the electron feel so specific that one naturally suspects there must be machinery underneath them. Surely spin comes from something spinning. Surely charge comes from some deeper arrangement. Surely such a rich set of properties must be generated by parts. That instinct is understandable. It is the same instinct that makes people look for gears inside watches and wires inside lamps. But nature is not obliged to honour the same logic at every scale. By the time physics reaches the electron, it begins to look increasingly possible that these traits are not the surface effects of smaller internal pieces, but simply the basic way this particle exists. That, however, is not the kind of answer the human mind accepts without a little resistance. Once you have spent time with all the odd habits of the electron, the next question presses in almost automatically. Fine, it has charge. Fine, it has spin. Fine, it obeys special rules and seems identical wherever it appears. But what is it made of exactly? Is there really no further layer underneath? Or have we just not reached deep enough yet? That is the point where the story turns from how the electron behaves to the more difficult issue of whether there is anything inside it at all. By this point, the question has become almost impossible to avoid. If the electron carries charge as a built-in property, if it has spin without literally being a tiny spinning ball, if it helps build atoms and chemistry and magnetism and the structure of matter, then what is it actually made of? What sits underneath it? What smaller pieces combine to give it these traits? Where is the hidden machinery? Because that is what the human mind keeps expecting. We are very used to the idea that important things are assembled. Watches have gears, books have pages, houses have beams and wires and plumbing, and at least one drawer nobody knows what to do with. Even in physics, the patterns seem to hold for a long time. Molecules are made of atoms are made of nuclei and electrons, protons and neutrons are made of quarks, so it feels almost unreasonable when the chain suddenly stops and someone says, with a straight face, that the electron may not be made of anything smaller at all. And yet that is, at least for now, the answer modern physics gives. Not because it has proven with final eternal certainty that no deeper layer can possibly exist. Science almost never speaks in that tone when it is being careful. It speaks in terms of what has been tested, what has been measured, and what the evidence presently supports. And the evidence so far supports a picture in which the electron is an elementary particle, not a composite one. It belongs to the family called leptons, and in the current best framework of particle physics, leptons are treated as basic ingredients rather than built objects. Official CERN material describes electrons as elementary particles, and CERN open data defines the electron as a stable elementary particle in the first generation of leptons. The current standard model framework also treats quarks and leptons as the building blocks of matter. That answer can feel a little unsatisfying at first, almost evasive. What do you mean it is elementary? Surely that just means we have not looked hard enough yet. And perhaps, one day, that will turn out to be true. Physics must leave room for that possibility. But the important point is that scientists have looked, and they have looked very seriously. They have smashed particles together at enormous energies, studied scattering with exquisite precision, searched for signs of internal structure, searched for excited, heavier versions that might hint at subparts, and searched for subtle departures from the behaviour expected of a truly fundamental electron. So far, none of those efforts has produced convincing evidence that the electron contains smaller pieces. The Particle Data Group continues to maintain dedicated reviews on quark and lepton compositeness searches, including searches for excited electrons and contact interaction limits, precisely because this possibility is taken seriously and tested experimentally. Those searches have not established electron substructure. This is a very strange place for the mind to arrive, because it asks us to accept a different kind of stopping point than the ones we're used to. When a proton is said to be made of quarks, the imagination is pleased. Good, it thinks, now we're getting somewhere. There are pieces inside. There is an explanation in terms of smaller components. But when the electron is asked the same question, The current best answer is not another set of pieces hidden one level down. It is more like this. As far as we can tell, the electron is one of the pieces, not a tiny object built from smaller little objects in the old intuitive way, but one of the basic entries in nature inventory. That shift is more profound than it may sound. It means the phrase, "what is it made of?" may itself be beginning to fail. For most familiar things, asking what something is made of means asking what smaller parts can be taken apart and rearranged. But a truly elementary particle is not elementary because we have become lazy. It is elementary because, within the theory and the experiments we have, it does not show evidence of being assembled from smaller constituents. Its properties do not appear to arise from hidden internal pieces in the way the mass and charge of a proton arise from the quarks and gluons inside it. The electron simply comes with its properties as part of what it is. That is hard to sit with, partly because it sounds almost too simple. Charge, spin, mass, identical behaviour across the universe, all of this, and no deeper mechanism made of smaller parts. The mind wants to protest. Surely a thing with so many specific characteristics must be built from something. Surely spin comes from something turning around something else. Surely charge comes from some tiny distribution within a little extended object. Surely there is a scaffold underneath. But the trouble is that these intuitions are inherited from the large world, the world of assembled objects and visible mechanisms. Nature does not promise to preserve those habits forever. One useful way to appreciate this is to compare the electron with the proton more carefully. A proton is not elementary. It has internal structure. If you probe it at high enough energies, you do not find a featureless point-like object. You find quarks and gluons, a dynamic interior, a distribution of momentum and charge, a complicated little storm bound by the strong interaction. The proton has size in a physically meaningful sense because it is composite. The electron, by contrast, is used as a probe precisely because it behaves as point-like to the best resolutions currently reached. CERN material discussing proton structure notes that electron-based machines use point-like particles, such as electrons, to probe the proton interior. That difference matters. The proton has a detectable inside. The electron so far does not. Now, point-like here has to be handled carefully. It does not mean the electron is literally a little geometric point you could draw with perfect certainty on a piece of paper and call that the final picture. Quantum mechanics has already taught us better than that. The electron can be spread out in a quantum state. It can behave like a wave in some contexts and produce localized detections in others. So point-like does not mean simple in every sense. It means that in scattering experiments and other tests of structure, the electron behaves as though it has no measurable internal size or subcomponents. There is no detected electron shell, no smaller charge lumps inside it, no evidence of pieces rattling around under the surface. It acts, to present knowledge, like a fundamental quantum object. That is why the answer to what is it made of exactly is both plain and unsettling. Exactly, according to current physics, it is not made of smaller known ingredients. It is one of the known ingredients. Not in a lazy provisional schoolbook sense, but in the highly tested sense that modern particle physics has a framework in which electrons are basic, and decades of experiments have not broken that framework on this point. That does not make the question foolish. It makes the question revealing. It shows us where our everyday intuition is still trying to force reality into the shape of mechanical assembly. There is also a quiet philosophical twist here. For a long time, people imagined that understanding meant finding smaller pieces. Break the thing down, name the parts, and you have explained it. That works beautifully up to a point. But elementary particles suggest another style of understanding. Sometimes to understand a thing is not to find smaller pieces inside it, but to understand how it behaves, how it interacts, what symmetries it respects, what fields it couples to, what role it plays in the larger structure of the theory. In other words, explanation in modern physics is not always reduction to little parts. Sometimes it is identification within a lawful framework. That sounds abstract until you realize we already half live with this kind of explanation. Ask what makes a chess knight a knight, and the answer is not what wood fibres inside it are made of. The answer is how it moves in the rules of the game. Ask what money is, and it is not just paper and ink. It is also role, system, relation, accepted behaviour. In a somewhat deeper and more physical way, the electron is identified by what it is allowed to do, how it couples to other things, what properties it carries, and where it sits in the structure of the theory. That does not reduce it to mere abstraction. It means its identity is not captured by the old model of a little built object with hidden nuts and bolts. Still, physics is not content with philosophy alone. It asks whether there are concrete signs that this neat answer might fail. Could the electron turn out to be composite after all? Yes, in principle. There have long been theories that imagine deeper layers beneath quarks and leptons, sometimes involving hypothetical constituents beneath the known particles. There have been ideas about excited versions of electrons that would signal internal structure, and ideas about new interactions that might appear if electrons were composite. That is why compositeness searches exist. Physicists do not merely recite the standard model and go home. They test whether its apparently fundamental particles are truly fundamental or only fundamental so far, and that phrase, so far, matters. It keeps the answer honest. The electron is fundamental so far. It is elementary in the present best-tested theory. It has shown no confirmed substructure in experiment. But science does not turn that into a metaphysical oath that no deeper truth can ever exist. If future experiments found excited electrons, or a measurable size, or deviations in scattering that pointed unmistakably to internal components, the view would change. Physics has changed before. Atoms were once thought indivisible. Protons were once thought elementary. Science would survive another demotion perfectly well, though many textbooks would require a difficult week. For the moment, however, no such demotion has occurred for the electron. That means the most accurate answer is also the strangest one. If you ask what the electron is made of exactly, the answer is not quarks, not smaller charged bits, not tiny loops or grains confirmed by experiment, not a miniature system with internal orbiting parts. The answer is that the electron appears to be a lepton with no known substructure, a fundamental particle carrying its charge, spin, and mass intrinsically rather than by composition. CERN educational materials and Fermilab public resources still describe the electron as an elementary particle, and current compositeness searches are framed as tests for possible departures from that picture, rather than confirmations that such departures have been seen. Now, one might reasonably object that this is not really an answer, only a refusal dressed in scientific tailoring. But it is more than that. To say the electron is elementary is not to say nothing. It is to say that the best account of the electron does not treat it as built from parts, and that its observed properties are not presently explained by inner constituents the way the proton properties are. It is to say that the electron belongs to a category in which the old question, what is it made of, may need to be replaced by other questions. What symmetries define it? What field is it associated with? Why does it have the mass it has? Why do there exist 3 charged leptons instead of 1? Why is its charge exactly balanced by the proton charge in ordinary matter? Those questions are not smaller than the original one. In some ways, they are deeper. There is also something a little humbling here. The world we touch every day is built from ingredients that may not all be little assembled objects in the intuitive sense. Some of them may simply be basic. That word basic sounds almost childish, as though one has given up just before the clever part. But in physics, basic can mean something extraordinarily powerful. It can mean an entity that appears in the laws as a primitive ingredient, one from which much else follows. The electron may be one of those entities. If so, then the visible complexity of the world rests partly on something that is not a little machine, but a fundamental quantum participant in reality. This does not make the electron less mysterious. It makes it mysterious in a sharper way. If it were made of smaller pieces, then at least the mind would know what kind of game it was playing. It would be another nesting doll, another box within a box. But if the electron is not made of smaller pieces, then its properties belong to the deepest level we currently know how to describe. Its charge is not produced by hidden charged grains inside it. Its spin is not the literal turning of subparts. Its mass is not simply the weight of constituents bound together in a tiny package. These traits belong to the electron at the level where the theory begins, and that is why the question remains so compelling. The answer is not merely no smaller pieces have been found. The deeper answer is that physics has reached a place where being made of something may no longer be the master concept. Instead, the electron is described as a member of a certain family, with certain intrinsic properties, governed by certain interactions, behaving point-like to current tests, and fitting into a framework that has survived enormous experimental pressure. That is not the end of curiosity. It is the point where curiosity changes shape. Because once you have accepted, even tentatively, that the electron may not be made of anything smaller in the ordinary sense, a new issue immediately rises into view. Fine, you may say, that is the present answer. But what exactly does present physics mean by calling it fundamental? How does the standard model place the electron among the known particles? Why is the electron grouped with leptons rather than quarks? What does it mean, in the actual language of modern particle physics, to say that the electron is one of the building blocks rather than one of the built things? That is where the next step becomes unavoidable, because the plain answer so far is nothing smaller we know of, only really becomes clear once you see how modern physics has organised that answer into its most successful framework. So this is the point where modern physics finally gives its most disciplined answer. Not the answer that feels most intuitive, and not the answer that makes the human mind instantly relax, but the answer that fits best with the most successful framework particle physics has produced so far. In that framework, the electron is treated as fundamental, not metaphorically fundamental, not educationally fundamental as a temporary simplification for beginners, but fundamental in the actual working sense of the theory. It is not described as a little object made from smaller little objects. It is one of the basic ingredients the theory starts with. That framework is called the standard model, and despite sounding like something one might purchase by accident when trying to upgrade a car, it is one of the greatest achievements in the history of science. It is the theory that organizes the known elementary particles and describes how most of them interact. It does not explain everything. It does not include gravity in the way physicists would like. It does not tell us why the universe contains the particular particles. It does in quite the satisfying way one might hope. It leaves dark matter, dark energy, and several deep questions still standing. But within its range, it has been astonishingly successful. It predicts the behaviour of particles and forces with extraordinary accuracy. It has survived decades of tests, and within this framework, the electron is not a composite object. It is one of the entries on the list of things from which ordinary matter is built. To understand what that means, it helps to see how the standard model organises the world. The theory does not begin with tables and chairs and trees and stars. It begins much lower down, with a set of particle types and interaction patterns. Among the particles that make up matter, there are two major families. One family is the quarks, the other family is the leptons. Quarks combine to form larger composite particles like protons and neutrons. Leptons, as far as present evidence shows, do not combine in that same way to form the familiar stable building blocks of atomic nuclei. The electron belongs to the lepton family. That already tells us something important. The electron is not in the same category as the proton, even though both are essential to the atom. The proton is composite. It is built from quarks held together by the strong interaction. The electron is not treated that way. It is a lepton, and in the standard model leptons are elementary. That means the theory does not describe the electron as having an internal structure, with smaller constituents inside it. There are no tiny internal electron quarks, no little charged gears turning in a hidden chamber, no known subparticles whose arrangement gives rise to the electron as a larger assembled object. The electron is one of the starting pieces. Within the lepton family, the electron is part of what is called the first generation. That phrase generation is a way of grouping matter particles into repeating patterns. There are 3 generations altogether. Each one contains a charged lepton and a corresponding neutrino, along with a pair of quarks. The first generation contains the electron and the electron neutrino, as well as the up quark and the down quark. These are the particles that make up the stable ordinary matter around us. The up and down quarks combine into protons and neutrons. The electrons arrange themselves around atomic nuclei. That is why the first generation matters so much for daily life. It builds the matter you and I actually meet. Then come the second and third generations. These include heavier relatives of the electron called the muon and the tau, along with their neutrinos and heavier pairs of quarks. These higher generation particles are real, measurable and important in particle physics, but they are unstable. They do not normally make up the long-lived structure of ordinary matter around us. So even though the standard model contains a larger cast than the everyday world seems to require, the familiar durable world is made mostly from the first generation. That includes the electron, which is the charged lepton of that first generation. Now, the odd thing about this arrangement is that the electron and its heavier cousins are in many respects remarkably similar. The muon behaves very much like a heavier version of the electron. The tau behaves like a heavier cousin as well. They have the same electric charge, they have the same spin, they participate in the same basic kinds of interactions, with differences tied to their masses and lifetimes. This is one of those places where the standard model feels both elegant and slightly mysterious. It does not just give us one charged lepton, it gives us 3, arranged in generations, with the electron being the lightest and the only one stable enough to build ordinary matter. The theory describes this structure beautifully, but the deeper reason nature chose 3 generations remains one of those questions physics still carries around. Still, for our question tonight, the main point is simpler and stranger. In the standard model, the electron is fundamental so far because it has no confirmed substructure. Physicists have tried very hard to find one. They have probed the electron in high-energy experiments. They have looked for excited states that might suggest an internal arrangement. They have searched for any sign that the electron behaves like an extended object, with a measurable size rather than a point-like elementary particle. Nothing definitive has appeared. The electron continues to behave within present experimental reach, like something elementary. That does not mean the standard model thinks of the electron as a tiny classical point in the ordinary visual sense. That would be too crude. Quantum theory already taught us better than that. An electron can be described by a wave function. It can be spread out in space depending on its quantum state. In atoms, it occupies orbitals, not little planetary tracks. So when physicists say the electron is fundamental and point-like, they are speaking in a more precise sense. They mean that the theory does not assign it internal structure, and experiments do not reveal compositeness. It behaves as though it has no known smaller parts. This is one of the reasons the standard model answer can feel unsatisfying at first. It is very clear, but it does not scratch the old intuitive itch. It says the electron is fundamental, but then the mind immediately wants to ask why this fundamental object has exactly the charge it has, exactly the mass it has, exactly the spin it has. It wants reasons beneath the starting pieces. The standard model can describe the electron properties and interactions with enormous success, but it does not fully explain why the electron exists with precisely those values, in the deeper philosophical sense. The theory is incredibly good at telling us how the electron behaves. It is less complete when asked why nature chose this particular entry in the list. That said, the standard model does more than simply name the electron and move on. It places the electron inside a very specific network of interactions. The electron responds to the electromagnetic interaction because it has electric charge. It also participates in the weak interaction. It does not participate in the strong interaction, which is reserved for quarks and the particles built from them. This distinction matters because it helps explain why electrons behave so differently from the contents of the nucleus. Quarks are bound together by the strong interaction into protons and neutrons. Electrons are not. They occupy a very different role in matter. The theory also gives the electron an antiparticle, the positron. This is another one of those features that would sound invented if nature had not insisted on it experimentally. The positron has the same mass and spin as the electron but opposite electric charge. When an electron and a positron meet under the right conditions, they can annihilate and produce other particles, often light in the form of high-energy photons. This is not an optional flourish in the theory. It is part of the structure of relativistic quantum physics, and it has been observed many times. The electron then is not an isolated little object in the standard model. It belongs to a broader pattern in which each matter particle has an antimatter partner. There is something very instructive about the way the standard model treats all of this. It does not ask what is inside the electron in the old mechanical sense. Instead, it asks what kind of particle it is, what quantum numbers it carries, how it transforms under the symmetries of the theory, which interactions it feels, and how it couples to the various fields in the model. This is a different style of explanation from the everyday one. It is not built around tiny visible machinery. It is built around lawful behavior and mathematical structure. To a physicist, that is not an evasion. It is the real content of what the electron is, and this is where the phrase fundamental so far becomes especially important. The standard model does not claim to be the final word on reality in every possible sense. Physicists know it is incomplete. It leaves gravity outside the main framework. It does not explain dark matter. It does not explain dark energy. It leaves several parameters, including particle masses, as inputs rather than deriving them from some deeper necessity. So when the theory says the electron is fundamental, that is the best current answer inside the best tested framework we have. It is not a declaration that no deeper theory could ever revise that status. Science has already taught us to be careful on this point. Atoms were once treated as indivisible. Later they turned out to have structure. Protons were once treated as elementary. Later they turned out to contain quarks. So it would be unwise to say with full metaphysical certainty that the electron can never be demoted in the same way. Perhaps one day a deeper theory will reveal that leptons and quarks are themselves built from something more primitive. There have been speculative models along those lines. There have been ideas involving smaller constituents beneath the standard model particles, but those remain speculative because the evidence has not forced the change. Right now, the electron remains fundamental in the sense that matters most in science. It is the simplest description that still matches everything we observe. This is also why the phrase so far is not a weakness. It is one of the strengths of science. It keeps the answer honest. It reminds us that knowledge is not built by pretending uncertainty does not exist. It is built by stating clearly what the evidence supports and where the frontier remains open. The standard model supports the electron as an elementary lepton. Experiment supports the electron as an elementary lepton. No confirmed data currently require us to insert smaller components inside it. That is the answer so far. There is a subtle but important difference between saying we do not know and saying the best theory says something specific. In the case of the electron, physics is not shrugging and wandering off. It is saying something very definite. The electron is treated as an elementary fermion. It has a fixed electric charge. It has spin of the familiar fermion type. It belongs to the first generation of leptons. It is stable. It has an antiparticle. It couples to certain interactions and not others. It behaves as point-like in experiments that would expose compositeness if such compositeness were large enough. That is a rich and precise description. It just is not the old kind of description based on smaller mechanical parts. This can take a moment to settle, because the human instinct to keep asking what is it made of is powerful. But at a certain depth, particle physics shifts the terms of the conversation. The better questions become questions like these. What is the electron role in the theory? Why are there 3 generations? Why are the particle masses what they are? Why do charges come in the patterns they do? Why is the standard model built from these symmetries and not others? Those are deeper questions than simply asking what smaller pieces sit inside the electron, and they point to something important. Fundamental may not mean boring or simple. It may mean we have reached a level where the right questions are no longer about assembly, but about structure, relation, and field. That last word, field, is where the standard model answer starts to become even more interesting. Because although it calls the electron fundamental, it does not ultimately picture reality as a bag of little hard particles floating in emptiness. The deeper language of the theory is field-based. Each fundamental particle is associated with a quantum field that extends through space. In that framework, what we call an electron is not best thought of as a tiny pellet made of something. It is better understood as a quantized excitation of the electron field. That sentence can sound intimidating at first, but it is actually the next natural step. If the electron is not made of smaller known pieces, then perhaps the real story is not about pieces at all in the old sense. Perhaps the electron is what the electron field looks like when it appears as a localized quantum event. That is one of the quiet revolutions hidden inside the standard model. The model still lets us talk about particles, because particles are what detectors register and what experiments count. But beneath that language lies a field picture. The electron field is one of the basic ingredients. The electromagnetic field is another. The quark fields, neutrino fields, and the Higgs field all belong to the same deeper style of description. In that setting, the electron is fundamental not because it is a tiny indivisible lump in the old mechanical sense, but because the electron field itself is one of the basic ingredients of the theory. This helps explain why the electron can be both particle-like and wave-like without falling into contradiction. A field-based quantum object naturally supports both sorts of behaviour. It can produce discrete localized detections and also show interference and spread. The older categories of particle and wave begin to look like limited glimpses of something more general. The standard model does not erase the electron mystery, it relocates it. It tells us that asking what the electron is made of may be less fruitful than asking what kind of field it belongs to and how that field fits into the broader architecture of reality. Still, we should not rush too quickly into deeper waters without noticing what an extraordinary position this already is. The standard model says that the ordinary matter of your body, your room, the planet beneath you, and the stars overhead is built partly from a particle that has no confirmed internal structure. A particle that carries charge and spin intrinsically. A particle that belongs to a repeating family of matter particles, yet is the only charged lepton stable enough to sit peacefully in atoms forever. A particle that is not explained by little inner components, but by its place in a larger quantum theory. That is a very unusual kind of answer, and it is one worth pausing with, because in a way, the standard model gives us both more and less than intuition wanted. It gives us more precision than intuition could have hoped for. It tells us how the electron behaves, where it belongs, what interactions it feels, and how it fits into the architecture of known matter. But it gives us less of the old mechanical picture. It does not show us hidden gears under the casing. It does not let us open the electron and find smaller objects inside. Instead it says, as clearly as present knowledge allows, this is one of the starting points, and that makes the next step almost unavoidable. If the electron is fundamental so far, and if the standard model is really built in terms of fields rather than old-fashioned little pieces, then the deeper question becomes not what smaller bits are inside the electron, but what kind of reality a field is in the first place. What does it mean to say that the electron is an excitation of an electron field? How can a field be the deeper thing, and the particle be the appearance we observe? That is where the answer begins to shift again, away from the old language of pieces and toward the stranger, but more modern picture in which fields, fluctuations and quantum excitations may be the real background of everything we've been calling particles all along. By the time you reach this part of the story, the question has changed shape again. Earlier it sounded natural to ask what the electron is made of, as though there must be a smaller object inside it, and then a smaller object inside that, and so on. Then the standard model answered as carefully as it could that the electron is fundamental so far. That still leaves a certain itch. Fine, the mind says. If there are no smaller confirmed pieces, then what is underneath it in the deeper language of modern physics? What is the more basic layer? And this is where particle physics gives a very unusual answer. Not gears, not grains, not hidden little beads, fields. In modern quantum field theory, what we call particles are described as quantized excitations of underlying fields, and those fields are treated as more basic than the old picture of tiny hard objects moving through empty space. Fermilab explains this directly in public material by saying that particles such as electrons and photons are quantum excitations of quantum fields that fill all of space. That sentence can sound forbidding the first time you hear it, partly because the word field has one foot in ordinary language and another in advanced physics. In daily life, a field sounds harmless enough. A field of grass, a field of wheat, a football field, though that one is usually less peaceful. In physics, a field means something more abstract and more powerful. It is a quantity defined throughout space, something that can have a value and structure everywhere rather than only at a single point occupied by a little object. We are already used to this idea in a limited way with electric and magnetic fields. A charged object influences the space around it. A magnet affects the region around it. The field picture says the influence is not merely a bookkeeping trick attached to distant objects. The field itself is part of the physical description. Quantum field theory pushes that style of thinking much further. It says the electron is associated with an electron field that exists throughout space, and what we observe as an electron particle is a localized quantum excitation of that field. This is the part that often feels almost backwards to common sense. Common sense wants the particle to be the real thing, and the field to be some kind of surrounding condition or mathematical helper. Quantum field theory invites the reverse emphasis. The field is not a decoration added to the particle afterward. The field is the deeper ingredient in the formalism, and the particle is the countable way that field shows up in experiments. A detector does not announce that it has seen a field in the ordinary way. It registers a discrete event, a hit, a track, a transfer of energy and charge. That is why particle language remains so useful. It matches what experiments count. But beneath that practical language, the theory is field-based. This helps explain why the electron has always seemed to slip away from simple classical categories. When it behaved like a particle, the old mechanical imagination thought it had found its footing. Then the electron produced interference and diffraction, and refused to act like a tiny bullet. The field picture makes that dual behavior less shocking. A field-based quantum object can produce localized detections, and also exhibit spreading, interference, and all the other wave-like habits that once made the electron seem contradictory. The contradiction was partly in our categories. We were asking whether it was really a particle or really a wave, when the deeper answer was that those two classical labels are both limited glimpses of a quantum field excitation. That does not mean one should imagine the electron field as a kind of invisible pudding sloshing around the room while little lumps occasionally pop out of it. That image is not an improvement. The field is not a material fluid in the familiar sense. It is part of the mathematical and physical structure used to describe reality at fundamental scales. Still, the idea of excitations is useful. A perfectly quiet field corresponds to no particle present in that mode. An excited field can produce what we identify as particles. For the electromagnetic field, those excitations are photons. For the electron field, they are electrons and their antimatter counterparts, positrons. This is one of the reasons the field picture feels deeper than the older one. It does not treat each particle species as a separate tiny kind of bead. It treats each as the quantized manifestation of its associated field. Once you begin thinking that way, the phrase, what is beneath the electron stops pointing towards smaller chunks and starts pointing toward the electron field itself. That is a very different sort of answer. It says the deeper layer is not another object hidden inside the electron, but the field of which the electron is an excitation. In other words, if you ask what the electron is made of in the old nested doll sense, the best current theory says that may be the wrong style of question. The electron is not like a proton, which has a detectable interior made of quarks and gluons. Instead, the electron is more like a fundamental mode of one of the basic quantum fields in nature. That is why high-energy experiments keep finding the electron to be point-like rather than composite. They are not uncovering smaller bits inside it because, in the present theory, there are no smaller bits there to uncover. There is something both satisfying and unsettling about this. It is satisfying because the field picture gathers a great many strange facts into one framework. It explains why the electron can be created and destroyed in interactions, rather than simply treated as an indestructible classical bead that must always persist as the same object. It explains why the vacuum can produce particle and antiparticle pairs under extreme conditions. It explains why the language of particles is sometimes insufficient, and why quantum theory insists on a broader structure. But it is unsettling because it takes away the old comfort of saying that reality is made of little things sitting in empty space. In the quantum field picture, space is not an empty stage with particles as the only actors. The fields are present throughout the stage itself. And then there is the vacuum, which becomes much stranger once fields enter the story. In everyday language, a vacuum sounds like nothing. Empty space, a room with the furniture removed, a perfectly clean absence. Quantum field theory does not let the vacuum stay that simple. Fermilab explains that even in vacuum the quantum field is still there, and it is never completely still. That means the vacuum in modern particle physics is not a perfect blank. It is the lowest energy state of the fields, but those fields remain present and can fluctuate. This is one reason physicists sometimes speak of vacuum fluctuations. The vacuum is quiet by comparison, not absolute nothingness in the old philosophical sense. Now, one must be a little careful here, because vacuum fluctuations are often described in popular science with more confidence than clarity. It is easy to drift into the idea that particles are literally popping in and out of existence everywhere in a simple cartoon way. The actual theory is subtler than that. But the important point remains: a quantum vacuum is structured. Fields remain. The lowest energy state is not the same as a total absence of all physical content. That is a profound change in how physics imagines empty space, and once you accept it, the electron begins to look less like a tiny object travelling through a dead emptiness, and more like one possible excitation, arising in a universe whose deeper fabric is already field-like. This also helps explain why the electron properties feel so intrinsic. Charge is not being generated by little charged grains hidden inside an electron shell. Spin is not the literal turning of tiny internal parts. In the field description, these properties belong to the type of excitation the electron is. They are built into the quantum numbers of the field and the way it transforms under the symmetries of the theory. That does not necessarily make them feel more intuitive, but it does make them more coherent. The electron carries its charge and spin not because it is assembled from smaller classical pieces that somehow average into those properties, but because the electron field supports excitations with exactly those characteristics. There is another important field in this story, and it answers a different but related question. The electron is fundamental so far, yes, but why does it have mass at all? In the standard model, the deeper answer involves the Higgs field. Fermilab public explanations note that the Higgs mechanism gives mass to elementary particles such as electrons and quarks, and later reports on Higgs measurements describe the Higgs couplings as part of the mechanism by which the Higgs gives mass to other fundamental particles. In this sense, the electron mass is not usually described as coming from smaller internal parts, the way much of a proton mass reflects the energy of its internal strong interaction dynamics. Instead, the electron mass in the standard model is tied to its interaction with the Higgs field. That distinction is quietly important. The proton and the electron are both matter particles, but their mass stories are not identical. The proton is composite, and much of its mass is associated with the energetic dynamics of the quarks and gluons inside it. The electron, being elementary in the standard model, is not understood that way. Its mass is part of the field-theoretic structure of the model, linked to the Higgs sector rather than to hidden internal constituents. So even when we ask what lies beneath the electron, the answer is still not smaller pieces. It is a network of fields and interactions, among them the electron field and the Higgs field. This is where modern particle physics becomes less like a craft workshop and more like an architecture of interlocking rules. The electron field is one ingredient, the electromagnetic field is another. The weak fields are part of the same broad electroweak structure. The Higgs field is another. Quark fields occupy their own place. Reality in this picture is not built from tiny billiard balls first and fields second. It is built from quantum fields whose excitations, couplings and symmetries produce the world of particles we observe. The standard model itself is described by DOE as the current best theory of the most basic building blocks of the universe, explaining how quarks and leptons make up known matter and how force-carrying particles influence them. The field picture is how that theory is actually formulated. At this point, the old question, what is the electron really made of, starts to sound a little like asking what a musical note is made of. If you ask in the right way, there are meaningful answers. A note can be described as an excitation in air pressure, or as a vibration of a string, or as a standing wave in a resonant cavity. But the note is not made of smaller miniature notes stacked inside it. It is a patterned excitation of a deeper medium. This analogy is imperfect, because a quantum field is not literally air or a violin string, and one must not push the comparison too far. Still, it points in the right direction. The electron is not best thought of as a little built object. It is better understood as a particular kind of excitation of a more fundamental field. This also sheds light on why particle creation and annihilation are ordinary parts of high-energy physics rather than impossible violations of common sense. In the classical little object view, creating a particle from energy can seem almost magical, as though a tiny bead had been summoned from nowhere. In the field view, it is less mystical. Energy can excite the relevant fields in allowed ways, and those excitations are what we count as particles. Likewise, an electron and positron can annihilate into photons because the interacting fields can change their excitation content. The fields persist. The particle content changes. What looks startling in the old ontology becomes more natural in the field ontology. There is a further subtlety, and it is one that makes the field picture even richer. The electron you might imagine in a simple introductory sketch is not isolated from everything else. It is embedded in a world of interacting fields. Because of those interactions, the electron in full quantum field theory is not just a bare abstract object untouched by the rest of reality. It is accompanied by the influence of the electromagnetic field and other quantum effects. Physicists account for this with ideas such as self-interaction and renormalization, and these are not minor corrections. They are part of why the theory can predict electron properties so incredibly well. One of the triumphs of modern physics is that this field-based quantum description yields numerical predictions for electron behavior that match experiment to astonishing precision. That success is one of the strongest reasons physicists take the field picture seriously. Still, a gentle warning is useful. The phrase deeper reality beneath the electron should not be taken to mean that every physicist agrees on a single, simple, verbal interpretation of what the fields are in a philosophical sense. Physics is often more unified in calculation than in metaphysics. The working framework is quantum field theory. The practical statement that particles are excitations of quantum fields is standard, but when one presses on what that means in the most ultimate philosophical way, people can shade their language differently. Some speak very directly as though fields are the primary reality. Others are more cautious and emphasize the formalism and predictive structure. For your script, the safest and most faithful statement is this: in the current best framework, the deeper layer beneath the electron is described in terms of quantum fields, not smaller confirmed constituents. That is enough to change the emotional tone of the whole question. Earlier, the mystery sounded like a mystery of hidden contents. What is inside the electron? Now it sounds more like a mystery of what kind of world could be built from fields whose excitations appear as particles. That is a more abstract question, but it is also more honest to the science. The deeper layer is not a tiny mechanical interior. It is a field-theoretic fabric with excitations, interactions, and fluctuations. The electron is one of the cleanest examples of this because it seems not to have an interior of its own in the composite sense. It points us away from the old image of matter as nested little lumps and toward a reality organized by fields. And yet, in a strange way, this does not make the electron less intimate to everyday life. It makes it more so. The electric current in a wire, the chemistry in your body, the structure of atoms, the glow of a screen, the behavior of magnets, all of it still depends on the same electron. The difference is that the electron is no longer merely a tiny object participating in those things. It is the particle face of a deeper field-based description that runs through all of them. The world feels solid and ordinary, but beneath that familiar surface, the theory says there are fields everywhere, never fully absent, capable of quiet fluctuations even in vacuum, and of local excitations we count as particles. That can sound grand, but it also returns us to the original question in a more precise way. What is the electron really made of? As far as present evidence goes, it is not made of smaller known pieces. In the deeper language of current theory, it is an excitation of the electron field, with properties shaped by that field and by its interactions with other fields, including the Higgs field. The old search for inner parts gives way to a picture in which the deeper layer is not another object but a field. The deeper reality beneath the electron is therefore not a smaller machine hidden inside it, but a quantum field framework in which particles are the discrete appearances of something more spread out and more fundamental. And that leaves us with one last step, which is perhaps the calmest and most difficult of all. If the electron is not made of smaller pieces, and if the deeper layer beneath it is a field rather than a miniature interior, then what should we say the electron really is? Not just within theory, but in the more reflective sense that first made the question interesting. If an electron is not a tiny planet, not a little billiard ball, not a proton-like object with a busy inside, and not a thing made of smaller things in the old way, then what kind of being is it in the furniture of reality? That is where the story finally turns from the search for components to the harder question of identity itself. So after all of that, after the glass tubes and the cathode rays and the strange behaviour in atoms and the wave patterns and the quantum clouds and the standard model and the deeper language of fields, we arrive at the question in its most stubborn form. If an electron is not made of smaller pieces, what is it really? Not what does it do? Not where was it first detected? Not how does the theory classify it? What is it? And the most honest answer modern physics can give is this: an electron is a fundamental quantum object, a stable excitation of the electron field, carrying a fixed amount of electric charge, a fixed kind of spin, and a fixed mass, appearing in experiments as a countable particle, but not behaving like a tiny classical lump with smaller moving parts inside it. That is the answer. It is not as tidy as saying it is a little ball of matter, and it is not as satisfying to the old mechanical imagination as saying it is built from smaller ingredients. But it is a real answer. It is what the best current theory says, and it is what the experiments keep supporting. Part of why this feels difficult is that the word really does a great deal of work in the question. When people ask what something really is, they often mean one of two things. Either they mean what smaller parts it is made of, or they mean what picture they are supposed to hold in their mind when they think about it. The electron resists both of those in the familiar way. It does not appear to be made of smaller known parts, and the right mental picture is not a comfortable everyday one. So there is a temptation to think physics has somehow failed here, that it has wandered into mathematics and lost sight of reality. But that is not what happened. Physics has not lost sight of the electron. It has learned that the electron is real in a way that does not match our ordinary habits for imagining real things. Consider how often, in daily life, understanding means taking something apart. If you want to understand a pen, you open it. You find the ink tube, the spring, the casing, the cap. If you want to understand a clock, you find gears or circuits. If you want to understand a loaf of bread, you can at least point to ingredients, even if the exact emotional role of bread in human civilization may require a longer discussion. We are used to explanation by disassembly, but not every kind of explanation works that way. Sometimes understanding means knowing the pattern, not the pieces. If you ask what a note played on a piano really is, the answer is not smaller notes stacked inside it. It is a certain vibration, a certain frequency, a certain physical event taking place in a lawful system. If you ask what a shadow really is, the answer is not a dark substance poured out behind an object. It is a pattern produced by blocked light. In those cases, the reality is not fake just because it is not made of smaller copies of itself. The electron belongs more to that second style of understanding than the first. It is not a tiny assembled machine. It is a basic kind of physical event or excitation that nature allows. That does not make it less real than a chair or a stone. In some sense, it makes it more basic. Chairs are made from atoms. Stones are made from atoms. Atoms contain electrons. But the electron itself, as far as we can tell, is not made from smaller known bits. It is one of the ingredients out of which larger material structures are built. This is where the field picture helps, not because it turns the electron into something vague, but because it gives us a better kind of reality than the old particle image could offer on its own. If the electron is an excitation of the electron field, then asking what it is really is a little like asking what a wave on the surface of water is really. It is not a separate substance riding on top of the water like a little surfer. It is the water doing something specific. In the same spirit, the electron is the electron field doing something specific. Of course, the analogy is limited. A quantum field is not literally a pool of water, but the basic point is useful. The electron is not a tiny bead made of hidden materials. It is a localized quantum excitation of something more fundamental in the theory. This also explains why the electron can seem to have two personalities. In one setting, it behaves like a particle. It arrives in a detector at a definite location. It transfers charge in discrete amounts. It can be counted one by one. In another setting, it behaves like a wave. It spreads out. It diffracts. It interferes. If you insist that reality must choose one of those old categories and stick to it, the electron looks contradictory. But if you accept that the deeper object is a quantum field excitation, then the contradiction softens. The electron is not flipping back and forth between honesty and deceit. It is simply not a classical object at all. It is a quantum object, and quantum objects do not promise to fit into the categories invented from stones and cannonballs. There is another part of the answer that matters just as much. An electron is not only fundamental in the sense of having no known smaller parts, it is also precise. It always comes with the same charge. It always has the same spin. It always has the same mass. Every electron is the same kind of thing. That sameness is part of what the electron really is. It is not an individual little creature with private quirks. It is a perfect, repeatable unit of nature. The electron in your body is not special compared with the electron in a star or the electron in a wire. It is the same electron in the physically important sense. Nature has one pattern here and uses it everywhere. That may be one of the strangest facts of all, because we do not encounter much in daily life that behaves this way. Two spoons may look similar, but they are not identical in the strict physical sense. Two leaves are not identical. 2 grains of sand are certainly not identical. Even 2 drops of water are not identical as total objects. But two electrons are not just similar examples of a type, they are fundamentally indistinguishable members of the same species. Quantum mechanics takes that literally. The world is not keeping little biographies for individual electrons. There is only the electron pattern repeating wherever the field is excited in that form. So what is an electron really? It is one of the basic repeatable ways the universe can contain matter and charge. It is a stable unit of negative electric charge. It is the lightest charged lepton. It is a fermion, which means it obeys the exclusion rules that help build the structure of atoms and the periodic table. It is a quantum object associated with its own field. It is detectable as a localized event and describable as a spread-out quantum state. It is not a little planet, not a miniature billiard ball, not a proton with a hidden interior, and not, so far as we know, a bundle of smaller ingredients taped together by invisible enthusiasm. The difficulty is that this answer asks us to stop demanding one particular style of picture. The human mind wants to ask, yes, but what does it look like? The honest reply is that what it looks like depends on how you probe it. In a cloud chamber or a detector, it leaves tracks or hits. In an atom, it occupies a quantum state with a structured spatial distribution. In scattering experiments, it behaves as point-like to the best resolution we've reached. In field theory, it is described as an excitation of an underlying field. None of these are fake. Each one is a different truthful handle on the same entity. The mistake would be to insist that only one of them counts as real, and the others are somehow only tricks. That is one reason the question "what is it really" can never be answered by a single simple image. Reality at this scale is not picture first and mathematics second. It is the other way around. The mathematics tells us what sort of thing we're dealing with, and the pictures are partial aids that help us talk about different aspects of its behaviour. If you want a comfortable picture, you can say the electron is the smallest packet of electron field that can appear as a particle. If you want a more formal answer, you can say it is an elementary lepton represented in quantum field theory by a spin-carrying field whose excitations correspond to electrons and positrons. If you want a simple physical answer, you can say it is one of the basic building blocks of matter and electricity. All three are pointing at the same thing. There is still a lingering objection that many people feel at this stage, and it is a fair one. If the electron is just a field excitation, does that mean it is less real than a solid object? Not at all. In fact, solid objects are the more complicated case. A chair depends on huge numbers of atoms arranged in a certain way. Those atoms depend on nuclei and electrons. The solidity of the chair depends on electromagnetic interactions and quantum rules, especially the behaviour of electrons. The chair feels more real only because it is easier for our senses to handle. But the electron is not less real because it is more basic. It is the opposite. The chair borrows its everyday solidity from processes in which electrons play a central role. This is worth saying plainly because quantum language sometimes gets mistaken for a kind of polite doubt. People hear words like probability, field, excitation, and wave function, and they imagine physics is telling them the world is ghostly or uncertain in the ordinary sense. But the electron is not ghostly. It is one of the most precisely tested things in science. Its properties are measured with extraordinary accuracy. Its behaviour under the relevant theories is predicted with astonishing success. The fact that the right description is not the one common sense expected does not make the electron vague. It makes common sense limited. There is also something deeply satisfying in the idea that the electron is not a little object with a smaller object hidden inside it, because it means the universe is not simply repeating the same design forever. The world is not just bigger objects made of smaller objects, made of smaller objects made of even smaller objects in the same style all the way down. At some point, the character of explanation changes. The deeper level becomes a level of fields, symmetries, quantum numbers, and allowed excitations. That is not a disappointing end to the search. It is a more interesting one. It means reality is not only built from things, it is built from patterns nature permits, and yet we should keep one hand on the rail of scientific caution. The answer is not final in the philosophical sense. It is final only in the scientific sense that nothing currently forces us beyond it. The electron may still turn out one day to have deeper structure. Science leaves that door open. If future experiments reveal excited electrons or measurable internal size, or some deeper layer beneath leptons, the story will change. Physics has survived such changes before. But we should not confuse the possibility of future revision with present ignorance. Presently, the electron is not waiting in some awkward half-known state. Presently, it is very well described by our best theory as fundamental. And perhaps that is the quiet conclusion the question has been pushing us toward from the beginning. Maybe the most honest way to ask what the electron really is not to ask what smaller thing is hiding inside it, but to ask what kind of role it plays in the universe. It is the carrier of one basic unit of negative electric charge in ordinary matter. It is the light, mobile partner of the atomic nucleus, the reason atoms have chemistry instead of just mass. It is one of the ingredients that makes light interaction, bonding, conduction, magnetism, and biological structure possible. It is part of why a star shines, why a wire warms, why a leaf reflects green light, why a thought can travel through a nervous system, why a screen can glow quietly in a dark room. That may sound as though we have answered the question by talking about what the electron does rather than what it is. But for something fundamental, those two things come very close together. For composite objects, you can distinguish sharply between the object and its behaviour. A watch can be opened, its gears can be listed. The function comes after the parts. For an elementary particle, the role and the identity are intertwined. What the electron is cannot be separated very far from how it behaves, because there are no deeper visible components waiting underneath to take over the explanatory burden. The electron is what carries these properties and participates in these interactions. That is not a weak answer. It is the kind of answer fundamental physics gives. So if you wanted one sentence to carry away into the quiet part of the night, perhaps it would be this. An electron is not a tiny chunk of stuff made from smaller bits. It is a fundamental quantum unit of matter and charge, best understood as an excitation of the electron field, real and measurable, simple in structure as far as we know, yet rich enough in its behaviour to help build nearly everything familiar in the world. And there is something unexpectedly comforting in that. The room around you may look ordinary. The blanket, the wall, the glass on the table, the wires in the lamp, the screen slowly dimming as the hour grows late. All of it seems calm and solid and familiar. But beneath that familiar surface is a world that does not work like the one our senses first suggest. It is deeper, stricter, and stranger. It is built partly from entities that are not tiny pebbles, but quantum participants, not little planets, but field excitations, not complicated by inner machinery, but by the exactness of the laws they obey. And the electron, so small that it cannot be seen the old-fashioned way, turns out to be one of the clearest signs that the universe, at its foundation, is not made of miniature copies of the everyday world, but of something more subtle and more orderly than that, something that has been quietly holding the visible world together all along,